Okay, I think it's connected to YouTube. Well, actually, it's processing. Okay then. So, it started. Let me. Okay. So, first, then let's start. Okay, first, thank you everyone to join this workshop or digital future engineer. So, okay, then to start, I gonna give you a lecture. So as a general content of the workshop, I'm gonna share my screen. This thing. So this workshop is called Hierarchical Modularity and Growability in Space Architecture. So this is about actually not primarily space architecture, but it's more about a kind of aggregation, kind of design of aggregation of a module in a hierarchical matter. So last year I ran another workshop. It was also about hierarchical modularity. But anyway, this year I'm gonna put that in the context of space architecture, and then but I'm gonna explain this out more later. But mostly it's the one aspect of the workshop gonna be I mean it's a technical workshop, so it's all processing, and then but the latter half workshop you wanna produce your design project of this kind of modular space architecture project. So then I'm gonna so that's the kind of general description of the workshop, and then the kind of schedule. This is 7 days workshop or 8 days. Wait, it's until July 2nd. We are meeting every day. So I'm gonna run several tutorial sessions today and tomorrow, maybe the Thursday. But the rest wanna be your project development. So each of you are expected to produce your design project. Then the tutorial part gonna be all actually processing, and then more specifically using the IGO library which I developed. Then, but today I'm gonna give you first lecture and the tutorial session. So the lecture is gonna be about the computational design engineer kind of, or actually more specifically for agent-based computational design. Then talk about the context of this space architecture, actually modular architecture design. So, technological aspect like a space engineering aspect a little bit. So let me start with first the lecture part. Then after that, I'm gonna run quick kind of self-introductory session with participants, and then we're gonna start the tutorial session. So first, the lecture about computational design. So then, okay. So this is going somewhere. Let me reshare the screen again. Even to another screen. Sharing, and I'm gonna share another screen. Okay, so as a kind of my self-introduction, so my name is Satoru Sugihara. I'm principal of ATLV, that's a computational design studio. And then I mostly work in facade design, like a complex facade design or building geometry optimization, and etc. And then so I've been a computational designer for maybe since 2007 or something. So then so one aspect of computational design is the kind of rational geometry, and then like making complex geometry simpler or rational, or at least buildable in a kind of cost efficient way. then usually I give a lecture about that other half of the part. But I'm focusing the other part, which is more kind of more exploratory into more newer algorithm or approach, which is agent based. So I want to talk about agent based computer design. So today, then. But in general, in my perspective, I think computer design kind of started when John Maeda started working design, in this case, graphic design, by text coding directly. So it was like 90s. And then, okay, there's other kind of trajectory to get to computer design as well, but this is one of the origins. And then, so when he was in MIT, or maybe he was sent to Japan. So he was working on graphic design using text coding, and then so I mean he was a computational computer scientist first, so he was not difficult for him to code, but he was running graphic design at the moment, so he was applying that skill directly to produce graphic work, and which kind of transformed. Well, it showed different quality or type of work, which kind of you can see in terms of like repetition and then quantity and the complexity. So those are the things traditional designer wouldn't produce by hand, but with computer, it's easy, and not only easy, but it's kind of essential for them to work in this way. So that's a kind of change the type of work or quality of work in a specific direction. And their success case areas came out of John Maeda's laboratory in Media Lab, MIT. So then he developed processing, and then that and John Maeda has a kind of educational tool called Design by Numbers, and that was for like students to learn how to code or how to design by numbers and algorithm. But Casey and Ben Fry developed that platform further to be practical for all type of creators to produce not necessarily computational design work, but some interactive work or computational design work to some real-time kind of dynamic expression. So that's kind of one trajectory to get to architecture. So then okay, then in architecture, so one thing, so usually I don't necessarily use a agent-based algorithm for functional design. So sometimes it works, and then this is a project by Morphosis where I used to work from 2017 to 2012, and the project is the Emerson College Los Angeles Center in Hollywood. So this facade, actually this is a courtyard facade, and then separating dormitory, private area, and courtyard space with these folded aluminum panels. So when I designed this, in the beginning, I wasn't using agent-based system, but at one point I had to use that to solve some problem. Problem was that, so I modeled in that way that those panel location was particle. Actually, so after we had the design direction, I remodeled everything in agent space, and then now panel location is based as a particle, and each of them connected by spring, and then the horizontal line, actually horizontal line also has a tension to kind of to go not too far, and then each lines are converted into panel geometry depending on the angle of the line. So that system exists, and then now that kind of responding system to actually they are interacting each other, and also it can respond to the environment. I mean, environment in this case, a virtual simulation space, kind of virtual force space. So I put the attractor field or repulsion force to control the layout or density of the panel layout. Then the problem I had was first, actually, obvious problem is the panel cannot collide each other, and the panel, I wanted to have the density kind of differentiation to be maximum. So the sparse part is really sparse and dense part is really dense. I mean, I already designed the panel shape to be like that as well, but on top of that, that's another kind of criteria. And then another thing is that there's a specific pattern we wanted, or we are interested to make it look like responding to other building environment. Actually, there's a central building in the project which has a very unique shape. So that that building shows a movement in other form. So we want that this facade to be kind of almost like a water surface responding to that movement or something. So, but anyway, that's another thing we want to design. And then yet another thing is when I thought about the perception of like when people walk on the corridor. So if all of the panel is closed in one floor, that's not that dynamic experience. So I wanted to have like an open and close and open, some kind of rhythm or some maybe minimum one kind of frequency or something. So I wanted to have that control, or actually that achieved by the layout. And then another one, which is serious one, which we couldn't avoid, is a smoke evac code. So to be safe, each floor needs to evacuate smoke. To do that, we have to have a 50% opening, or more than 50% opening. So that's one of the hard constraints. So to achieve all of the constraints at the same time, I use the particle system to as a soft solver. So kind of solver to algorithm to solve a problem. But soft means it does the at best, meaning they don't necessarily achieve all of the goal. So they try to achieve. But I had that I mostly control the like parameter potential, etc., and also the force field, like attract allocation and the strength of them. So to achieve the problem at the same time. So can play with that and then. But anyway, that's how I applied the agent base to the facade design. So as a soft solver. So, but this kind of approach, so that was kind of virtual force simulation. And then force simulation, I mean, nowadays super popular thing or easy thing to do, especially with a grasshopper kangaroo. So that's not, I'm just using that new, but you can easily produce a minimal surface type of or anish upper type of shape. Or this is a bit more towards not really engineering, but the traditional mesh relaxation problem, meaning the mesh kind of spacing to be not too different. So you can use the tension simulation to distribute the difference around the shape. And then in the traditional way of direct modeling, you cannot do that, but with this you can do to adapt to the very unique boundary condition. And so because you already have the kangaroo and those are the physical simulation system, so you wouldn't model that by yourself. But if you want, it's not that difficult. You can do that. Just simply implement all the kind of Newton's law equations. That's all. Or can do the simulation. So, but anyway, so I mean, physical simulation is one kind of agent-based algorithm. So this, and you could also apply that to other algorithm, or actually combine with other algorithm. But anyway, so physical simulation, well, in the beginning, like it was popular thing to use that for form finding. But form finding is basically like to find a form under certain condition. So boundary condition, environmental condition, material condition, etc. So that I mean, you have some of those conditions, and you want to see what form would work best with under the condition. So that's how you do it. But it's not new technology. I mean, Gaudi did that with a physics model, and so. But these days we can do that easily with digital too. So you don't necessarily need to do that as well. Meaning, if you want to stick to physics and you want to think about the structure seriously or somewhat seriously, you would need to stick to the actual physics rule. But if you go further, I mean, architect, you are supposed to go any direction. So you can make up fantasy physics through somewhere, kind of, I don't know, not even alien, but anyway. So these days we have that freedom. Like a digital simulation, you can do the physics, but you can do like unrealistic physics or anti-realistic physics if you want. But that's the kind of digital to capacity. But anyway, so like a swarm simulation is kind of that. I mean, swarm algorithm is kind of found in 80s, 70s. So in the Hollywood movie industry. Then what was it game? But anyway, so that was a kind of upright architecture in certain time. Then, but this is like one type of particle which can move by itself under that kind of void rules, and you can. But using that is one thing, and by using that to build geometry is another thing. So there's many different ways to build geometry out of swarm. I mean, yeah. So in this case, they kind of they connect line to neighboring agent, then just keep moving up. So that's one thing you could do. And then this is just graphics, but the swarm. So this is also kind of the swarms are paired to neighbor, and they keep to right. Actually, no, it's not paired. It's just drawing the line to the close one. So the same thing, but the kind of motion happened, or actually the interaction to produce certain mixture happen. There is very specific way of kind of expression, or like kind of its movement, but the plus its gradient thing from static to dynamic. So rule are same. So they are just following the same rule all the time. But anyway, so this kind of agent approach usually generate the emergent type of geometry, which these days you can imagine what's emergent geometry like, because we went through that kind of architecture design for a while. So then certain complexity, certain kind of specific local condition, and several different conditions. I mean, usually several. Then so you can use that. In this case, branching algorithm is applied to structure of convention for that was the competition for where was it? Changsha in China, which I think that at the end of the how build something. Then so then this one is not agent based. This one is actually something I taught at Hierarchical using Grasshopper Python. But this is about the subdivision. So subdivision algorithm actually not. It's simple technique, just dividing one face of mesh into different shape. That's all, and then you divide again and again and again. So I mean, this is not agent based, so it's not applied to the topic I'm talking right now. So I'm showing this to show certain type of complexity. Like a complexity is still kind of vague idea, and then maybe still kind of a issue worth talking in architecture. Actually, even it's too general topic, but there's many different type of quality or complexity. The thing I want to point out is it's complex, but there is a certain homogeneity and heterogeneity at the same time. Well, actually, that's one thing. So chaos is one thing. Usually, chaos means complex, but you see no order. It's kind of flat. It's chaos is usually have white noise quality. Actually, white noise quality means it's everywhere same messiness or something. So there is no like a dense part and sparse part, kind of equally messy. That's usually chaos. But there is organized chaos as well. So actually, that's the things. One of the thing in the key quality we want to focus in the workshop. And then so there's a difference. There is a similarity. So there's a consistency, but there's also heterogeneity or kind of differentiation happening. So in this case, I mean, you see some type of geometry and the other type of geometry, and there's a weird kind of plant-like thing, and those. But you also see certain kind of unifying, not really atmospheric, but even geometric sense. For example, like a scale is kind of similar. I mean, scale differential is one thing, and the geometric differentiation or kind of integrated consistency is another thing. But that kind of aspect is carefully controlled by designer, in this case, like students. But that's something I want you to have as designer sensibility. So we are still pursuing, or this workshop gonna pursue certain type of complexity which has quality of consistency and the diversity at the same time. So then going back to agent base. So this is agent-based algorithm to produce mushroom gel. So in this case, students investigate the growth process of mushroom gel and then simulate it to produce that. Then of course, I mean, as a designer, you want to tweak it to generate something you would want, or a designer would want. So, but this one is kind of still kind of mushroom shape. But not so this wasn't exactly the algorithm wasn't exactly developed for, well, I think following the actual scientific biological algorithm. This is actually a combination of swarm algorithm and the branching algorithm. So those lines of kind of swarm kind of moving from center to peripheral location, but if they are kind of too far each other, they produce new branching geometry and actually new branching swarm agent, and then they kind of keep growing. So then neighboring agent keep projecting surface underneath, and then that surface has a weight actually only in the middle point, and then that keep falling down by gravity. So that combination produces this shape, and then this is another example of bacterial movement simulation. And this is also a combination of swarm simulation and branching. So there's a kind of parent swarm, which kind of root swarm just going outside, and there's several generation of child agent, the yellow one and the purple one, they go inside. Although they are also, I mean, they are following the swarm algorithm as well, so they have alignment behavior or cohesion behavior, etc. So then once you set up the system, you kind of explore the parameter space to change the behavior to generate something interesting. So that's one approach. Another example is this is a simulation of a fractal broccoli, the Romanesco, the weird fractal shaped vegetable. So the simulation of that is kind of fractal. I mean, it's because the geometry is fractal, the behavior fractal. So you produce a kind of spiral agent, and then the child of spiral agent make a small spiral agent, and the child of spiral agent create small agent, and then by everybody kind of keep growing. So that's one thing. Urban simulation, or urban, in this case, migration simulation through history is something you could do in agent, and then to see what happens. I mean, you develop agent algorithm to in comparison to the history, and then when you get something similar to history, then you can simulate something in hypothetical setting. And another type of urban agent simulation, in this case, just urban habitat. I mean, each agent is simulation, but like each people in a city, in this case, Bilbao. So there's a several different type of agent walking around or running around, although I think they are all supposed to be pedestrian speed. They have different behaviors. One kind of like a local resident behavior, like they stay home, they go out to shopping or grocery shopping, etc., and then maybe go back to their home. And another would be like a tourist agent. They get out of hotel and then go to museum and then go to restaurant and the bar, etc. And then there's another. Actually, I forgot another one. But each of them kind of have different behavior, and so they have a sequence of destination based on their behavior. Then put them all over the place and then see what happens. Meaning, mostly this is a kind of problem finding simulation for traffic. In this case, we can see where is a kind of more congested location, or most of the time in Bilbao it's a bridge. when you simulate this. And then another thing you can find as a problem is some shortage of program. Like there's a certain group of people trying to go someplace, but it's very far and it's taking time, etc. So actually, those are lines kind of those straight line shows the destination of the agent, meaning those are people trying to come here, although they're kind of wondering there is no bridge here. So that kind of thing. So but anyway, so that's one type of agent-based application. And this is another that's a project with Jose Sanchez, and I mean he developed a game called Blockfoot, and this is a kind of initial version or kind of research version of that. We did that in Smart Geometry Hong Kong 2014 or something. Then, but anyways, I joined the project and I was developing agent system. So he was developing like this whole urban simulation game, or actually urban design game. So user or game player design urban space or city. Then they were in a very similar way with the SimCity. And then in this case, kind of grid based, and you put a block in each. And then there's a two evaluation system. One is a static, which is like a certain combination of a program, certain kind of neighboring or adjacent kind of block has certain effect, like putting some program and some program together work better, or some putting some and some doesn't work better, or if city has certain ratio of some program that's good, not bad, like energy emission to energy consumption, etc. That's one thing. That's static evaluation of the city. Another evaluation is dynamic evaluation by agent. So this kind of human agent kind of working around. So similar to the previous simulation, they have behaviors. They want to sleep, they want to go, or they need to go to work, they need to eat, etc. Or they need to go to park to relax, etc. Then so they have the desire, or actually desire. Then if it's not fulfilled, and then that's stress, and then that stress gives some negative score to the evaluation. So that kind of thing. So that's one application of agent system. And then going back to more kind of abstract geometric realm. So this is just swarm simulation, but this swarm agent changes its behavior constantly. Although it's actually all choreographed, meaning they are changing the parameter by time, and each time, or actually, so that's time frame this, the parameter is this, and time frame this, the parameter is this. So as a result, I mean, you can clearly see the separation behavior is different at some point, and then cohesion, I mean, something coming together is different, etc. So that's a result. But anyway, so that kind of specification of the agent parameter is just, I mean, that's one score, and then but those are the result. Geometry is kind of continuous thing because they didn't jump to location. They just change the behavior tendency, and then they still need to respond to the environment in other neighboring agent. So that's how it came out in this way. Then another issue would be like this type of agent-based system. Oh, actually, this is the swarm algorithm. Swarm algorithm is, I mean, fascinating to some people at some point, but it's kind of difficult to apply to the architecture. Then because it's complexity and then lack of operationality. So I had one challenge to build something like that. But to do that, it's not, of course, it's not easy because some of them kind of not really unbeatable, but not efficient. And then that those form are not necessarily works well for structure. So there's to build that I had to have another agent simulation specifically for structure optimization. So there's two agent system. One is a swarm agent system, and another is a structure optimization system. So I mean, each of them agent algorithm. So swarm agent is just flying around freely, or just following swarm algorithm, and then but there's two structure optimization agent. One is the kind of vertical lines, and with the swarm kind of leading, and another is a horizontal line, and that's actually horizontal one is a compression simulation agent, and the vertical one, top to bottom, is a tension simulation. And then when you see those lines are kind of moving around, that's the process they are optimizing. So when they kind of stop, that means the structure is in equilibrium. So at least this can hold in as structure under gravity. So without that, yeah, the form gonna change. So but anyway, so that's the one type. So agent based, so there's a two agent based working together. The one is more kind of exploratory, and another is optimization. So you can use agent on both sides. And same thing for another project to design a peer. And in this case, so there's a swarm simulation. In this case, I run simulation in two different steps. So first step, just for swarm simulation to make geometry or form, general form or formation. And then second is optimization. The optimization is by that the compression and the tension simulation. So it kind of go. So right now it's slowly moving. That's the process of trying to find the equilibrium state, which would work well the structure. And yeah, that's, I mean, basically that just removing the extreme condition to kind of distribute the problem everywhere, kind of equally. So then each of them can take, hopefully. So that's one approach. Then, okay, another agent based. So this one is a cell division algorithm. So for several years in the past, there's some kind of a trend of using cell growth algorithm. But I mean, I had my own interest, and I kind of developed that from scratch. And actually, that was because of the branching algorithm. I thought branching algorithm a bit weird that each branch doesn't grow usually. I mean, they branch, but each length of edge stays same. But that's weird. So I started kind of exploring that each line grow as well, and then that kind of somehow ended up a cell growth algorithm. But anyway, so each cell in this case represents as a circle or just point, and then they divide into two. But the thing is that when you divide into two, where do you put that cell in relationship to other neighbors? So this one, the cell growth algorithm I developed is specifically has a static determinant topological information, meaning that they know where they are connected, which cell are connected or not connected. It's the analogy to the cell junction or like the so actual cell biological cell have that behavior like connected to other cells. So but there's many other researchers and architecture designers develop the cell growth algorithm. Some of them, actually most of them, doesn't have the static topological information. They kind of connect to the neighboring or cells. And then, but anyway, so in this case, I was interested in the topological manipulation or like a topological growth. So I was playing with that topological mechanism. So meaning the who to connect to when, kind of thing. So that mechanism, there's a variation of the mechanism, and then each of them produce different type of geometry through growth. So this is, I mean, this is 2D, but just connecting to, just inserting the new, I mean, your child to just neighboring agent, and they just keep connecting and create this kind of shape. And then this one creates the type of geometry like kind of fluffy geometry. When you put the child cell to the center of two neighboring cells, then it creates this kind of pointing geometry. And then, but this is assumption like cells are forming surface always. So in that case, all the cell has a face or like a triangular face, a polygon mesh face, and then so the issue was where to put the child cell on that face. Then this case, putting in the middle of two triangle, kind of midpoint of two triangle, which creates not boxy, but like, I mean, it has certain angle, but it's less pointing from last time. Actually, the one funny thing is that I thought in the beginning I would make a sphere by growing cells. And then that was somehow one of the hardest things to do. I couldn't make a sphere easily. So I could just produce like a pointing, like a sharp geometry easily, but smoother one, it was difficult. So this was a kind of trajectory to figure out how to make the smoother faces. And at the end, what happened was like topology needs to be like in the beginning, it should be like hexagonal kind of alignment, actional alignment. So thinking about like 6 surrounding neighbors and then putting that new agent or new cell and then sharing the half of the giving half of the neighbor to child agent and the other half to be still on the parent agent, and then somehow made that made the geometry smoother. That was one finding. But anyway, so the point is there's a bunch of mechanism, like a topological mechanism to switch, and then that's that generate different type of geometry, and there's a kind of process to explore that, and there would be some geometry could be worth using for certain application, or actually that kind of thing is still question. But anyway, so mechanism or like algorithm of a topological switch, and it corresponds to very different classes of geometry. That's the thing. So, but anyway, that's I mean, this is a branching of polygon mesh faces or body. So then this one is a kind of still also branching, but it's a group of cells, a group of cell branching together. So like, yeah. So there's a certain co-working relationship between the group of cells, and then I mean they cannot grow without neighbors, but they can branch to group, etc. So but anyway, so that was one exploration. I mean, just developing your own new agent-based algorithm. So this is an example of that as well. So then start thinking about, in my case, I was interested in topology, so I mostly work on that level. And then there's also the issue of what to do in architecture. So this is one case where I applied that to design sealing installation, actually the lighting installation, kind of lighting diffuser. So in this case, that growth process was corresponding to the condition of I mean certain complexity, and I mean first of all, making the form interesting. One thing is the kind of this topological kind of donut shape, not really donut, but like a little bit Möbius type of switch, but growing that shape into different geometry. And then, but in this case, the below is kind of, I mean, this is installation, so giving some kind of artistic, atmospheric thing to the space. So expressive geometry comes to the bottom, but the top part, you don't see much. So we wanted to keep the simple for the cost efficiency. So the top part is super simple, or panel is big, and the below is a more divided small panel. So I made the condition, like the growth condition, like a certain z coordinates correspond to the growth rate. So the bottom lower z higher growth rate, and the upper part not lower growth rate. So that kind of control is happening in that cell algorithm space. But anyway, so there's other thing like other aspect of digital fabrication, and then so our physics simulation. Actually, this is quite similar to the previous structure optimization. Then for digital fabrication, producing each triangle by piece, that's one thing, but the quantity of the parts would be inefficient. So combining together is another thing, but combining together to what maximum size and like a laser cut. But in this case, yeah, pieces are cut in laser cutter. So there's a bed size limitation. So these are strip panelization. So combining the triangle into one. Then the direction is also controlled. I specifically set up the algorithm to do this spiral panelization, meaning concatenating the triangle together. So then, yeah, panel packing is another sheet, part packing is another thing, and then then production. So that's the result. But anyway, so but the main thing will be like the cell growth part, but other part will be there's several different algorithmic process involved to produce them. So, and then slightly different type thing to talk, which is like agent-based algorithm or agent-based computational design tends to produce some kind of organic shape or kind of nature referencing geometry or quality. So that's actually one thing which is natural to think is that this algorithm came from nature in the beginning. Or so this approach, agent-based approach, originated in complex system science in 70s or 80s, and then but at that time, yeah, that came from observation of nature, I think, or like butterfly effect. I mean, butterfly effect is out of mathematics, meaning like some mathematician is checking the formula to predict weather, and I think that was a story. But anyway, so but like to check the number if it's correct, and then just to reduce the time, he used slightly simpler number to calculate, but it produced totally different number. I mean, for the pressures, so for weather testing. So I thought he calculated wrong, but he wasn't wrong. Like a slight change in those complex system. I mean, in this case, system means equation, like a very complex mathematical differential equation to predict the air pressure of the whole Earth, or not the whole Earth, but some location. So it's like a it's in the area of fluid dynamics. But anyway, so that kind of thing was kind of found in science, and then scientists also find all the behavior in nature, or like cell behavior to kind of botanical behavior to the animals to many things. Then then swarm came, and then although that wasn't by scientists, and then algorithm found by other person, and then so we kind of designers started use this, and then that kind of naturally came to that organic thing or nature looking geometric quality. However, that's not only thing architects are interested in. So another contrasting aspect or different type of geometry in architecture history is this more like artifact quality. So I mean, in box cubes up, you can also think that as a part of quality in mathematics or some kind of a conceptual realm, but also this history of human culture of artifacts and pyramid to shrine to I don't know, some historical artifact. So, but there's also complexity there. I mean, you can have like a minimalistic cube, but at the same time, you can see the very complex grid in the urban space, etc. So that's two different kind of camp or interest in architects would have. However, the thing I'm interested is that they are not opposing thing, I mean, in my mind. So for example, even the urban space, like ancient urban setting in like the left bottom part, I mean, you see the houses are square, although the whole layouts are not. And because that's an incremental development, a historical reason to all the local issues led that whole geometry or urban geometry being a bit, not necessarily organic, but not orthogonal. So that you see certain kind of a bottom-up sense there, or kind of historical agent-based system like thing. You can imagine people are kind of struggling, and maybe you could point out which parts started first and which came later, and it's the collision location, etc. So that incremental logic of bottom-up could be inside kind of artifacts kind of quality. Also, but I mean, still kind of choice, meaning choice of the designer to produce. However, if it's kind of incremental phenomena, you kind of have no choice other than like you have power to give the top-down instruction. So, but anyway, the thing I want to propose as a designer is that kind of that's continuous thing. Like one side, super top-down artifacts like square, doesn't need to be square triangle, it could be triangle, but very top-down strict rule, but other bottom-up. But I would say that's seamless. That's one just spectrum. And then, but that this decision, bottom-up versus top-up, top-down, even in the algorithm level or design level or like work organization level, there's a many issue of that, like something which can be solved easier in bottom up, something which is easier to top down. So many people are thinking about combining together, which is something. Although there's a certain kind of trade-off, meaning you might lose some quality to do that. So, but I'm suggesting is that hierarchy. So without like just not like try to have the balance of two things together. I want to say so my approach is the same bottom up. Starting point is still bottom up, but to achieve certain bigger picture or bigger organization, I'm introducing hierarchy into bottom up. So that's a algorithm I'm developing like past several years. So that's a hierarchical bottom up. That's the algorithm I'm calling clock stack algorithm. Still in development, but that's the thing we're gonna use in the workshop. So, but anyway, so what I'm interested in is hierarchy. Also, okay, so the idea is that the agent is a behavior in time. It's not geometry. It's the things to do in time. But in the past, there's a certain simplicity in agent-based design, or like Swarm, mostly like a Swarm-based design system. There's a certain kind of degrees of kind of uniform quality, like a white noise or chaos, not chaos, but white noise quality, meaning there's a kind of very similar, consistent rhythm everywhere. So, but that would be because the agent behaviors is all uniform, meaning all same all the time. So what if you can change the behavior? I mean, not like a 2 or 3, but like very hierarchical all the way. So meaning so to do that, I introduce like a hierarchical clock, like stack of clock. So you don't have just one clock body in agent body clock. There's a kind of bottom level clock. So in this case, agent moves on the toward the right when the bottom level clock increment. But when the second clock kicks in, you do something else. I mean, agent, in this case, agent turn 90 degrees to the left. And then again, the first level, like bottom level clock moves and then go straight. And then, but again, the second level clock ticks and then turn again. So so you have 3 level clock, and then actually when you come back, the third one ticks. But anyway, so it's like every second agent does something, but every minute agent does something else, and every hour agent does something another, and then every day, every week, every month. So each defined clock level of clock still kind of maintains all the kind of detailed thing, but still have the bigger module. So basically one module higher level clock creates bigger module. That's an idea. So for example, so that this is a simulation of the algorithm or behavior I just mentioned. But if you have another clock branching, like every second turn, every second straight, every minute turn, and every hour, in this case, every hour branching, and then every day, the branching part is turning 90 degree, and every week the branch happened again, and every month another branching happens. So, but anyway, so that's the kind of hierarchy I'm talking. And so each hierarchical level, you have defined parameter to control. In this case, the top level branching have every day or every month level or fixed level something, you change that turning the angle to 60 degree or 120 degree. And then in this case, the bottom level, every second level, you change the angle to turn like a 0.1 degree or something. And then even kind of deeper angle. So higher level stage. So this is the agent trying to make like the square of square grid system. And then behavior is still same, but only the bottom one, like where agent supposed to go straight, it didn't, it turned a little bit. And as a result, the whole square of square urban, not really urban, square of square grid system turned into this circular system, although which is kind of still grid. I mean, topologically, they are all still carrying the exact same quality with orthogonal grid. But anyway, so even you want to introduce randomness, you can introduce randomness at different level. This one is introducing the randomness to the highest level. So the branching happen, or the biggest branch happen in the different timing. In this case, middle part is having the random thing to like the square, like a middle size square is a different size because of that randomness introduced that level. And this one has lower level introduction by randomness. So like the smallest square size is different because it just, yeah, that level random turn happens. I mean, random timing of turn happens. And then this one, like a two different randomness, like middle randomness, and then the highest level randomness is in angle. So the highest turning is slightly off 90 degree. And this one is the lowest straight line is now angle is not straight. So kind of everything. Actually, no, this here has like a 2 or 3 different randomness in different level. So, but anyway, so that's a type of randomness. So, but anyway, this is a collection of geometry or using the algorithm. So, actually, this level kind of relates to this workshops. I'm gonna run this video whole thing, maybe like 2 minutes or something, and then yeah, you can just watch, and I'm gonna just take have some coffee. Then, but anyway, so this one is like actually no, each of them different, right? So yeah, so the issue, not issue, but point is like you see the bottom up building process, but also you see the module as well. So you have like for example, there's a square and a triangle, or this is like a hexagon, but you see the biggest hexagon as well. Although that hexagon is necessarily you placed at once, it was kind of bottom up process to build the module. So if something like if the environment changes, or if some other agent comes, they can stop in the middle of construction of the big module. So meaning each of them maintain the adaptivity, but you also have the efficiency of a bigger module as well. And then bigger module would turn into different module based on the condition, so possibly. And then this one is making cube, although I mean this one actually agents are kind of right now, well, this one is line based. So to make face, it was making a spiral, and then this is just 3D-dimensional branching. And then, but that 3D-dimensional branching is changed by changing the angle, and this is more triangular, well, something. But triangular spiral module and branching. But anyway, so and this keeps going. This is kind of trying to look like some protein or something. But anyway, so yeah. But this is more square, and then trying to make space something. So that's one thing. And this one I'm gonna talk about later. And then okay, save some more example of like, so this is a student work from SciArc, and then yeah, using that algorithm and to produce specific type of geometry. But anyways, this was the exploration of the type of geometry, and then aggregation of that. So yeah, some of them have that kind of artifact quality. Some of them look like I mean, these one look like leaves. Although that kind of this adjustment of the like mostly angle, somehow angle has huge kind of visual impression of like a 90-degree angle has very strict artifact looking, and then slightly off any off angle tends to generate a nature looking thing. But anyway, but it's a gradient thing. So if you want one thing, you can do you can control to the other, or you can show both if you want. But anyway, so that's the thing, and then this is like workshop, digital future workshop last year, and then it was actually the topic was more inclined to the context, like historical context, like thinking about or picking some elements from the historical or cultural context, and then try to incorporate with that to generate or propose this hierarchical modular system. So indeed, one of them is like this roof tile looking or agent roof tile looking thing, kind of expand into agent branching system, and then although I mean, we stay like abstract geometry, so it's just all line work, 3D or 2D line work, and but so this actually this and the previous one is kind of a one work in a different setting. So there's a kind of range of the possibility there, and then so the first one is a very strict kind of angle turn, and then but this one, the second one was more organic looking. Also, you see the topological connection is kind of same. And this is another student's work, and then actually this was actually this came from the inspiration for of like a Chinese tea or something. But anyway, so this kind of cube allocation is happening all over. Okay, so that was the end of the first part of the lecture. Actually, yeah. So now I want to talk about more specifically about this workshop, and this is one presentation. Okay, let me go to the second presentation, which I think I need to share the screen again to the another screen, which is first. Let me stop sharing screen, and second, let me start another PowerPoint. Then let me share. Okay. So the second part is about the robots, and then so I'm gonna talk about like a kind of background technological context, and then okay. So the second part of the lecture is about modular robotics. So this year, I mean, we are still we're gonna still work on processing, and then we're gonna work on that hierarchical modular geometry algorithm, and then I mean that algorithm to produce hierarchical modular layer. Although we are thinking in the context of a space architecture using modular robotics. So this is a kind of technological background, and then just for you to have certain alignment with reality, we don't really go for full realistic technological proposal, but we kind of don't want to go far totally sci-fi. So yeah, for you to know those idea. Then so there's a history about self-reconfigurable modular robots in robotics, and then since 80s. So the earliest example is like in 80s. So basically, there's a robot. I mean, usually non-humanoid robots, or actually even, I mean, robotics system or even cybernetics system. There's an issue of like whole and parts. Like making for humanoid is one thing, or as one thing is one approach, but you making humanoid out of multiple parts is another thing, and then making non-humanoid from module is yet another thing. So that there's a certain idea in robotics or mechanical engineering and robotics, and to make robots out of module, not like So each they are individual robots, but they combine together to function differently as well. So there is a one. So then there is the issue of like mobility and also connectivity. So that was kind of main issue of that in that area. So in in 2000 there's a magnetic connection, but this so each of robots has a different type of movement as well. So some of them have each wheel and they can move by itself. But this, for example, this one molecule, they don't move by themselves. They move through connection and through assembly of that. So they only first connect to the other module by magnets, I guess. And then main movement is a one rotational movement running diagonally or in the axis of the diagonal cubic vertices, and then that creates like as by combining several robot modules together, they can function as robot arm, and then the end piece can move to other location as a result of movement of robot arm, etc. So kind of connection to movement and the whole kind of really choreographed move, all those still kind of bottom up in a way, is kind of a result of a kind of collaboration of multiple robotic agent or robot module. So another example is it's this one, like this I think also magnetic or but anyway, so this one is a kind of the previous one is a kind of diagonal rotation is a main movement in module, and then this actually in this case module is one module is a black and white piece. They are combined together. So the with the kind of central in the middle. But anyway, so that's mainly the rotational movement, and then through connection. In this case, this assumption like kind of transforming into like a snake robot to four leg robots to possibly humanoid. So that kind of transformation is kind of an assumption, well, kind of direction it was going. But so that was one example, and the another one that is Atrium. In Denmark, and that's I mean slightly different alignment or like a grid system, not really orthogonal grid system. It's more like a MC type of like hexagonal, not really hexagonal, but so diagonal kind of kind of crystal formation can be achieved, and then there's a very specific type of mechanical joint there, and then actually I think joint move, and they also each module also kind of rotates. So this is like a flattened ball looking, but that they move around the plane, the flat plane. So that middle section is kind of the metal ring is the location separating the one side to other to move or rotate around. So it can actually function as a wheel as well. So there's a multiple kind of like way to move as well. But anyway, so that's I think another thing, another history in robotics is like a Symbrion. I think it's was a huge project involving many universities, but so that they are kind of each of them I think can move. I'm not sure that, but anyway, that so they can aggregate and then combine, and they can make a bigger structure, and then they can move differently, etc. So that's a kind of really one of achievement to have the like simpler small pieces, but as a aggregated body, they have achieved different kind of higher function. And then swarm robotics is another, I mean, slightly different type, although which involve higher quantity, and then then one huge kind of one research project which had a huge impact to the world was this Kilobot Harvard University. That I think it's Kilobot, its name is Kilobot because they use 1,024 robots, but each piece is super simple, and super simple mobile capability, and they kind of vibrate, and then with that three, and then they also have very limited simple way of communication. I think infrared communication, so to neighbors. So but the main kind of achievement is that simple communication, there's a specific algorithm to achieve the bigger behavior. So in this case, I think they can form the whole pattern into show some letters or some figure by giving very specific instruction, or when agents or each robot has very specific algorithm to achieve. So through that behavior, they can achieve a kind of bigger behavior, but still staying keeping each robot to be super simple. So that's one thing. And then even in drone, like Intel developed drone, I mean, this is for kind of commercial purpose for the lighting festival installation. However, the kind of algorithm to involve that is actually, they are not simple, but there's a certain way to like avoid collision, to the choreograph whole thing, but at the same time, but actually no, the level of kind of control is now kind of achievable in this level. I mean, not kind of individual non specialist level, but there's a technology kind of example. Yeah. And then the kind of successor to the Kilobot, they are currently or recently developing this soft robot, meaning this one is also the behavior simple. Each robot also is kind of the plastic disc around one on the top is the kind of expand and contract. That's the whole thing robot can do. So it's and the contraction and expansion sometimes catches the neighbor with the kind of the interlock pieces, and then once it's locked, when you expand, I mean, it pushes the neighbors, and then contract, and yeah, you also influence the neighbor, and but that process is kind of the only thing each robots do. But as a group, when you do that, as a group they can move through the contraction expansion of specific order, or actually that part exactly, I don't know. But as a group, they has a much higher level of behavior. And then like right bottom image is like when you have, I mean, simulation, when you have like more than 1,000, I don't know how many, but pieces, and there's a very specific algorithm, and to do what in this case they try to move from one side of the wall to the other, but the wall kind of apertures are limited, so they kind of all of them cannot move at once. So there's a certain behavior there. But anyway, so that's a kind of research in robotics, I mean engineering area. And then in architecture, we saw those robots working in the past, and like ETH did drone construction. I mean, they already done the robot construction, robot arm construction, but they also have this distributed fabrication system using drone. And then another one, this is at Harvard, and then this one is a kind of brick stacking robot. Actually, it got the inspiration from the termites or some type of ant, nest building ant. But so I mean, this also have, if you look into the each behavior, it's kind of simpler than you would think. Although, I mean, it's not, I don't think I can build this robot like in a short time period, but still like behavior and mechanism is simple. So that's one thing. And then in having like a recent development, like University of Stuttgart, like computational design, ICD produced this research project, and then so these are kind of timber construction robots. Although the robot, each of robot is super simple. I mean, not super simple, but they carry that, but they don't only locate the timber material to the location, but they also use the timber materials to as a body of robot as well. So when you like two of them connect, two modular robot connect together, they can kind of walk as well. And then with three, with four, they have certain behavior. And then of course, but the goal is to construct a wooden building. So both of them kind of integrated together. And another impressive research is that at the MIT mediated matter group, they build this kind of growing, kind of pipe growing robot with fiber. So fiber and then UV light curing, and then the robot inside the pipe, but the robot creates pipe. So then the robot can move forward inside the pipe, so it can keep growing towards the upward towards the direction. And also they have the control over the angle as well. So that kind of thing. Then and another one, not necessarily in architecture, but this is kind of building us this is for architecture construction. So this is at MIT, and then the Center for Bits and Atoms, and then so this one is like robots. Also, robots movement is supported by material, but robots are to move the material, so they kind of work together. So material and the robot work together to build something. And they also have another robots inside a lattice. So so I mean, this is a lattice assembling robots, and also there's a robot on the left image inside the lattice. That's a kind of lattice maintenance robot in case of something needs to happen, like after construction, if something needs to happen inside, or fixing, maintenance, or something, building something, or delivering something. There's another kind of robot there developed, and then that's quite impressive research as well. So that's one thing. That's still, I mean, that was in architecture, although actually with robots. But so that was for construction. So it has a robot and it has material. But there's an area like robot is material. Robot is building block. So in this case, actually, this is still using like a material and something. But this mostly robots try to become part of a structure. So it's not like just constructing something, although for efficiency reason or speed of construction, this combines the material as well. But most of the time, the robot is material. In this case, furniture scale, but some robots are already built, and then so similar to some other self-configurable modular robot I've shown before, like this is kind of cubic module, and it rotates diagonally, and then there's a connectivity between, and then to make some, in this case, to make a chair or table or some furniture. So that's one example. And then, but like robots, or like a self reconfigured robot being building block is that the research is really extensively done by Architecture Association, the Spirable Studio, like for more than 10 years. So he's quite pioneering in this area. And then I mean, with students, they deal with many different type of modular robot and the possible aggregation of that and the application. So actually, one of them like is assuming like the space architecture, so similar to our kind of topic. And then others like a cubic or spherical shape, and then some of them assuming magnetic connectivity, some other are using mechanical joints, and then some of them applied to like a domestic environment. Other like responding to like program changes during the day, etc. Or yeah, etc. Or some modular bigger. So but anyway, so it's kind of modularity, or like a connectivity, like a actual mechanism of connection, like usually is a magnet or mechanical joint connection. And the another is a mobility, like actually another is actuator, like a sub motor, or more like a thrust type of like a linear movement, or pneumatic mechanism, etc. That kind of explored there. And then also the type of movement they can do. So some of them could move by self, but some of them could move only through the connection, through the aggregation, and certain coordination of multiple modules. So there's many aspects of the kind of research happen there. So then some of them sometimes deal with the issue of like a logistic, like how module could go there. So like module, if module can move by itself, then module can go there by itself. But if cannot, say that you might need like a mechanism to deliver the module to there. But then maybe you might use the module to deliver the system as well. But anyway, so that kind of a thing is there. Okay? Then another thing I can show is that there's a modular robots research in space context as well, and then in actual like a space engineering field. So this is a kind of modular robots for I think it's to unfold the antenna system. So like delivering module or like an antenna module or solar panel kind of module to space and then unfold is very traditional challenge in engineering. And then, so this is one approach that like even like every antenna is, I mean, this is a kind of fabric material is folded into the module, I mean robotic module, although the robotic module is assembled in space by itself and then unfold. So there's several steps there. But in this case, actually this is this one module, one robot module doesn't move itself. In this case, I mean the image is super low resolution, but this one is using the another robot. So actually this hexagon thing doesn't move by itself, or it doesn't have the actuator inside. I think it might have that for the unfolding, but for the movement or for the aggregation of the module, this kind of black linear thing is the actual robots to move things around. So I think those, so it's kind of robot arm. So those robot arm moves around the module and they move the module as well to aggregate those modules in space. And then once it's done, it's kind of, I think, expands to make a antenna or something. So that's one thing. And another example is actually this one is using the research from MIT, but the NASA is also working with them to think about the scenario of the space architecture automatically built by robot, by this modular robot. Actually, I think they are trying to like make a prototype soon. But so scenario is you send multiple. So in this case, also construction robot, distributed construction robot. So material and robot are mostly separated, but they send material and then kind of super exchange right material to carry, and then also send a modular robot to assemble them, and then put into either space or in Mars or Moon or some other planet, and then let them build some space, maybe for astronaut to come later or something. So that's happening. So but anyway, so that's the kind of technology exists there. So with that context, we want to kind of think about our design project. So then I gonna explain the design project a bit further. Although it's kind of anything, but anyway, let me open another PowerPoint. So then another thing would be just so another thing, I mean, the workshops again is gonna be about this kind of hierarchical aggregation, and then so but anyway, so the image is something I already shown, but the assumption is like wait. Okay, assumption is like so module will be like shipped so the spaceship and something, and then like then connect to the some of the module, and then the module move around the module to build something. So that's kind of a kind of assuming scenario, and then but the thing I gonna ask you to do is like designing the module and then designing the movement and designing actually movement not much, but the behavior, the whole behavior to assemble. But the main focus is going to be about the whole the quality or hierarchical quality in aggregation. So this, but showing those are not necessarily good example, but you can imagine the current international space station. It's I mean, we can see the pipe and then the stretch, or there's several different components, but maybe not focusing that, but you can imagine one singular module and connect it again and again with there's a branching joint, branching component, and to connect several different direction of module. However, you kind of see kind of in terms of hierarchy, if you assume using the hundreds of module or thousands of module, some kind of flat relationship might not be. I mean, that's one thing be fine, but another thing, you can imagine something more interesting or something which might have a better function or some certain other quality when you think about the higher level of kind of hierarchical module. So actually not module, but in the sense of robot, but some component which is made out of 80 module, which creates certain type of either space or function or something. So in this actually, so again, the image I'm showing not necessarily a good example. It doesn't involve any function, etc. But each component is a kind of cubic module. But you see these squares which might have function, might not, and then you also see the circle of squares. So, but anyway, so that kind of hierarchy is something I'm interested, or I'm interested in you producing some use of hierarchy in kind of for something. So giving some function doesn't necessarily function, but a certain different quality, kind of novel quality, which we don't see in the current conversation or even in sci-fi context. So, but anyway, so that's the whole layout, and then like a visual quality to convince the quality of hierarchy as something novel and important is something we are interested in. But that's main thing. But other thing would be thinking about a module shape and then assuming the module and the connectivity and the movement in terms of kind of scenario, not really proposing actually how to move in terms of kind of magnetic connection or some mechanism you can think about. And then so that's kind of a direction of the workshop. And as an example, I mean, this video is not for this workshop, but I made for other purpose. But so this is kind of a type of presentation making showing the component. Actually, first explain some level of kind of movement and connectivity images, and then showing potential mechanism, and then potential aggregation and the potential process to aggregate. So this kind of thing is something I want you to produce at the end. So actually, towards the end, the design project. So design project is about to design this whole aggregation, hierarchy aggregation, space architecture modules. But for as a deliverable of workshop, I'm gonna ask you to produce a short video, like 1 or 2 minutes, or something like, not something like this, but showing the whole aggregation as a kind of main focus, but talking about the module shape, module mechanism, not, I mean, to kind of simpler level, and then some reality check type of diagram, something I've shown, and then possibly showing the process of growth, not really growth, but how they move around the module, which I have some code to automate super simple one, but if you develop complex movement, I don't really have. But anyway, some movement, and then the final aggregation is a kind of final result. So maybe big rendering or something. So that's something I'm gonna ask you to produce. Actually, big rendering I don't have in this video. So, but anyway, I'm gonna talk about this again after tutorial, maybe after second Thursday, again about the what kind of thing you need to produce at the end. But as a direction, this is the direction we are going, like a modular robot aggregation, but not necessarily main focus in the actual robot detailed design, but somewhat convincing design, but main focus is the aggregation, the whole aggregation. We want to see some type of hierarchical aggregation we haven't seen before. That's a kind of goal we want to pursue. So, okay, so let me stop the presentation part. So okay. Then the next thing we're gonna do is maybe first I can talk with you guys, and then if you guys have any question about any of the part of presentation, I can answer, and then after that I think we're gonna go around the introduction of each participant. So if you have, or any of you have a question, you can just speak up. Then don't forget to unmute the mic. Then, if not, I can have the self-introduction. So I'm gonna ask each of you to introduce yourself, and then you can show me some work of yours, and I mean you can you talk and you can show some work. So okay, I only see like a login name on the Zoom, so I think if I to let other people share, I think I need to allow that. But anyway, okay, let me call your the login name, and then please print that. Okay, first, Aroni Roy, can you self-introduce your name and then kind of short description your background and work?
Hi, my name is Orni Roy. I'm from Bangladesh, and currently a master's student at the Royal Danish Academy in the Computational of Architecture. I've been practicing architecture for many years, and I graduated in 2015. And ever since then, I worked in Vietnam in Vô Trong near architects and many architects in my own country. And throughout my experience, I felt like the future of architecture has a lot to grow and develop with the help of computation, because the cities, especially from Bangladesh, where I come from, it's I would say Dhaka is one of the is a hub of chaos theory in city terms. It's a beautiful miracle, and that almost 23 to 25 million people can live in such a small area of land. And that kind of inspired me to go into studying computation and how it could go into kind of developing the future of architecture because of our fast-paced city. For my practice, I guess I could show you my portfolio, and it's on Vimeo. So my background, my parents are both artists, so I work in multi dimensions rather. So most of my work is very much influenced not just with the different landscapes of architecture, but also incorporate my practice with multi-dimensional knowledges. And well, I wouldn't go much into it, but yeah, this is first year works at my university. And so when I was actually making my portfolio, I thought that portfolio is a very much an expression of the self, and tangible world is just as important as the digital. So I kind of made a portfolio where you could hold it and experience the multi-layers of design. And I tried to incorporate while looking at the design, like sections, uh, kind of like the project unfolding in itself through the portfolio.
Looks good. All right. Thank you very much, dude.
Yeah.
Yeah,
Thank
good.
you.
All right. Thank you. All right. Let me call other person to self-introduce. We can wait. Next, Jerun, can you do the self-introduction?
Hello.
Hi.
I'm Jerun. I am a PhD candidate at the Sapienza University of Rome, and my research topic is concerning space architecture and in its development in a very sustainable way. And currently, I'm working on construction methods with in-situ resource materials. And this is the reason why I enrolled in this workshop, which I find really interesting. And I think I can learn a lot from my PhD path and research. And I have just one work related to space architecture, and it's actually a design contest that I participated with a friend of mine. And it is about a very simple structure. Oh, no, I can show you. Which is that, a sort of donut. And the idea is by rotating, it can create a certain of artificial gravity. And the circular form may improve the internal space perception, and can therefore to improve the user experience. One of idea, it was that there can be many aggregation of those forms forming a sort of space community or neighborhood. And this the idea was that it can bring a new idea of a space community and a settlement for human colonization of the space. Yeah, that's all.
Good. All right. Thank you very much. Okay. And then next, can Giuseppe Bono, can you do the self-introduction?
Yeah. Hello, everybody. My name is Giuseppe, and I'm at the moment a candidate in architectural computation at the Bartlett.
Do you have video camera? Your camera is off, although if you cannot, that's fine. But
unfortunately, seems it doesn't work.
okay, all right.
I always have problem with Zoom. So sorry for that.
Okay.
And yeah, so I'm, as I was saying, I'm studying at the moment architectural computation at the Bartlett, and I'm doing at the moment a work that is related to self-reconfigurable robotics as well. Okay. So yeah, and yeah, I'm looking forward for the workshop. Thank you.
Great, thanks. All right, next, Ina or Aina Shevios? Can you?
Ina Kitwash, yes.
No? Okay. Yeah, go ahead.
Hello, everyone. Thank you so much for the presentation. It was very interesting. I'm a PhD candidate in the Grammatical Research Group. And I will just share my screen a bit to explain a bit about my background. Previously, I worked in digital fabrication for additive manufacturing. So, for example, in this case of the urban cabin at those architects. Then I work at ESA for the development of certain additive manufacturing materials for a lunar habitat. And now I'm working on the environmental parameters of additive manufacturing robotic fabrication of a facade. So I'm very interested in the modular growth and how that can be applied for a space habitat. So yeah, looking forward to the results.
Good. Thank you very much. All right. Next, Nisha Wood, can you do the self-introduction?
Hello, can you hear me?
Hello.
I'm a student now in first grade for math and I'm majoring in architecture. I have a typical English, so I will show my portfolio.
Right. Actually, the connection doesn't seem to be stable and the voice wasn't good. But wait, can you show? Yeah, stuff. Yeah.
Yeah, I'm still so.
Right. But no problem. Go ahead.
That's all.
Yeah, we see your screen no problems or your voice doesn't come through, but I think you can keep showing your work. Well, I guess that's all. Right. Okay. Then yeah, actually, yeah, I think the network connection issue maybe so we didn't hear well, but fine. So, but anyway, thank you again. Then the next Shoko Ikemoto, can you show your work and then self-introduction?
Hello everyone, I'm Shoko Ikemoto. I'm a graduate student in Japan. In my university laboratory, I usually do research on the history of Japanese traditional architecture, but I'm also a member of a creative team called ND3M. I designed a space with a focus on computational design. I'd like to introduce two works. So the first work is a small pavilion that combines units made by 3D printing on cloth, taking advantages of the expansion and contraction of the cloth and 3D printing. And we realized a hard and soft material. The second work is a project to create a dynamic ceiling by attaching a complex wooden structure. All the parts are designed using rhinoceros grasshopper and cut out using CNC. I joined in the workshop because I was interested interested in robotics and space architecture, and I would like to create a work of art in with digital fabrication as well. Thank you.
Thank you very much. Okay, I think that's all. Like we have 6 people, although I see we are supposed to have 7, though I don't see another. So we move on. This participant. Okay, so okay, then now we move on to the tutorial. So I think I'm gonna do that. Okay, I'm gonna start a technical tutorial session with processing. And I assume everybody already installed the processing on IGO library. And then is that working on everybody's computer? Is that no problem? Okay, then the thing we're gonna start with is, and then first let me share my screen. Okay, then so I'm gonna go through some of the tutorial. Although I'm gonna kind of start simple. Actually, first let me go to this website. So this is the library, IGO library website. Although it's not safe, but I mean, yeah, but it's working. So I'm gonna go through some tutorial today. So actually, I asked the participants to go through some of them. Plus, I require participants to have some coding understanding experience. So I don't need to start from the very start. But the agent part, I still want you to be kind of familiar with or getting comfortable with like multi-agent aggregation stuff. So that part I want to start simple today. But the plan is that today I want to go through not all of them, but like some of simple like a line stuff, geometry aggregation through behavior. Actually, the point of the tutorial is really about understanding of super simple transforming operation, like moving forward or rotating 3 degrees or something. Then the result of that. So because this is agent-based bottom-up, and then result is usually emergent, meaning unforeseeable. Well, actually, it depends. If you have tricky operation, result is unforeseeable. But I want you to develop the sense of foresee unforeseeable. So that's kind of the process. The point of the thing. The point of the tutorial session. But so first I might start, I mean, with those some of them, and I think I today want to do the branching as well. So branching is one trick to do. I mean, of course you branch out and the quantity multiplies and like in exponentially, but at the same time it's also about the interaction. So in this workshop, I don't ask you to code interaction behavior because it's very tricky and then complex. Though understanding that would be important for you for your further work development in the future. So I'm gonna do some today. So maybe I think I'm gonna do this 2 part like a modular reproduction rule design and then branching. 2 things I'm gonna go through the rest of 2 hours something. So then tomorrow I want to go into that algorithm I was talking about, the clock stack agent algorithm. Then I'm gonna explain that, and I'm gonna ask you to not to go through, but like practice. And then but this really go into the actual topic of the workshop, and then but this, I mean, geometry wise still super simple, meaning actually this is surface, but geometry is kind of still simple abstract, like line or point, or could be some surface. But after this, maybe in the 3rd day, currently I haven't put out on the website, but I'm gonna put the example to map your design geometry and module geometry to agent. So you can actually now put the agent in, then grow together. There will be some simple animation of how it can be animated, the delivery process. Actually, that part still I'm working on that. I can just show you example right now. Actually, I was still coding this thing, but like for example, something like this. I mean, there's a lines developing, but the robots are moving around that. So this one, so animation, that is something I can give you as a tool for you to develop. In this case, this is for presentation purpose. The design part will be done by just whole simulation layout. However, but anyway, so however, these are some limitations. I mean, each technology has some limitations, and if you want to maximize the result, you kind of need to balance the whole thing. But so this one, I want to give you this code later, like in the third day, but there's a limitation, meaning some cheating. So there's some unrealistic simulation there as well. But anyway, but that's a plan. So today, simple agent and branching, and tomorrow, clock stack agent algorithm. The third, we go into the kind of modular robot, module aggregation, module geometry aggregation. So that's the plan. Then actually this code gonna be heavy. So today, start simple. So I'm gonna go into this again on the igeo.jp tutorial website, and I'm gonna go into tutorial page, and then go into multi-agent algorithm, and I'm gonna start with this multi-agent algorithm update with vectors. So actually, in case I want to give you a bit more kind of general introduction to this library. First I'm going to start another file, but so I mean, processing interaction I don't give, but this algorithm, no, actually, this library, IG library, is has several aspects. Multi-agent algorithm kind of template is one thing, but other part of general geometry modeling, you can do that there too, because I initially made this for facade design, or not necessarily only that, but so the generating surface, controlling that, panelization one thing, and then all the technique to differentiate the shape, geometry, transformation, etc. That's all there. And then so you can deal with, you can generate basic geometry, points, lines, nervous curve, nervous surface, polygon mesh, B-reps that you can generate there. Although each of them have certain specific instructions. So if you are interested, you can check in some of the examples there. But actually, in this workshop, I don't think you're gonna need to do that, because I set up the template to import space module geometry from Rhino cells. So later in the third day, you're gonna model geometry in Rhino and import that to this processing IO. So that's what happened in this code. This is importing geometry from Rhino, so that's the geometry is imported from there. So then, so you don't need, but in case if you are interested, the tutorial, or actually the instruction there. So then, but the other half of the library is about the multi-agent system, and then one agent system is this. There's two different type of agent, multi-agent. One is a kind of self-reproduction agent, meaning so each agent kind of stayed one location. They don't move. So those are the agents which don't move, but they produce child agent next to it. It doesn't need to be next to it, but a certain direction or a certain location, and then aggregate. So the quantity just increase. I mean, you can delete them if you want. You can instruct them to kill themselves if you want. But so that's a kind of agent. Another set of agent is agent which can move around. Usually this is a kind of supposed to be particle based, so like a point, movable point is a kind of called conventional particle in a way. So particle base and then swarm agent is one sub class of that. So it can move and it can also like have the behavior to move closer or further based on some rule. So the page we are going to use today were reproduction based, but there's a whole other set of agent based system in the end tutorial there. So if you are interested, I mean, not in the workshop, actually, if you have a way or think about a way to integrate them, yeah, go ahead to do. But there's another whole other thing about movable kind of particle based agent. And then sometimes you can combine together as well. But anyway, so today we focus on this, and then we start with this multi-agent algorithm vectors. Then let me jump to some section. I mean, now assuming, I think you guys in general like computational skills are quite high compared to the average, and then so you have understanding of mechanism or algorithm, but maybe just specific instruction commands you don't necessarily know that. So maybe first this code. So I'm gonna once the thing I'm gonna do is I'm gonna copy and paste some of the code and explain that what's happening in each line and each command. And I expect you to follow that and just to see what's happening. And then at some point, I'm gonna ask you to change some codes to do your own thing or just some exercise of geometry. So that's a kind of format of the tutorial. So the first thing I'm going to copy and paste is this one, like a second code in the, actually no, third code in the page. 2, 3. So that this straight line. So I'm going to copy paste this code to my processing window. Copy and paste, you can I put several buttons, but some of them don't work. So the left one, I just select the whole code, and you can, this one doesn't copy yet, so you need to copy that. So then I want to paste into the processing stage. So maybe first let me run this and then see what happened, and then let me explain what the meaning of each. So this one is just a drawing line. And then first of all, if you have any technical issues, this would be the time you might see the issue. But hopefully, if you don't have problem, usually when you see so in processing, so on some of them, some of you, are good at some platform, but maybe new to processing. In processing in general, if anything goes wrong or was wrong, the text message on the bottom want to show some red text, and so if you see some error, that actually sometimes it's already shown that, but when you the code is fine, but something happened in the simulation, like 10th agent collapse or something. If that happens, some red text might show up, and then that's some issue you might have somewhere, or some behavior issue. But anyway, so okay, let me. So code-wise, I want to talk about specifics. Including some fundamental specifics of code first, and then even from the input. So for example, this part you never change during the workshop. So but so you don't need to write, but just for understanding that the import part, the first 2 lines are to import the library. Actually, in processing 3, you don't need the OpenGL import there already there, but necessary for processing version 1 and 2. No, actually only 1. And then usually processing has the section called setup, that function or procedure or method. So that's the part processing code start the program. That's the first thing to do. And then in processing, you are supposed to set the size of window first. So that's what that's supposed to do. And then that's the also moment you need to kind of second process of importing the library to there. Then this one is just controlling the simulation period. You don't need to do that. Usually, if you do nothing, the the simulation never ends. It just keep going. And then most of the time what happens is just keep going and the geometry more complex and getting slower and then maybe might get to the maximum memory and then crash. But if you don't need to limit the simulation time, you don't need to put, but if you want to limit, like you can put this duration method, ig.duration. So this IG library has tons of class and the method, but some of the command is start with IG, the capital I, capital G, and the dot, and there's a method, there's a many method there, like a time related, simulation time related, or the whole library related command are there. So yeah, well, like for example, if you want to change the background color, that's trivial thing to do, but you can also actually do that. You can also do that like RGB color and 00 meaning black. You can make the background black if you want. So, but anyway, so but just this is a kind of format for method or IG library kind of macro level control. Then in the setup, another thing you usually need to do is you need to create a first agent, like a first generation agent, like a starting agent. So, but the actual agent is defined below. So that's a class definition. And usually in processing community, the code writing policy is that when you have defined the class, you might separate the file or tab. You can do that as well. So usually usually you separate the tab or file, but the reason why I'm putting them all together is because just for tutorial to see at once. So that's kind of my tutorial type of template. So if you want to separate, you can. If you know some processing and you have your own way of code writing, you can do that. But I kind of stay there. But in case if you separate the code in a different file or different tab, this is a way you do. Usually you name another file with the class name you are creating. So the tab, new tab you can create here, or you can create somewhere. So then usually you create the name with agent with that class name. Actually, I don't. I'm just showing the examples. I want to delete this file, but when you make the tab, usually this is the location you put the whole class there, which if you prefer you can do, but you don't need to do. But the behavior, of course, code behavior doesn't change. So, but I gonna maintain this code here. So then I'm gonna delete this tab. But anyway, so but anyway, the important part is there's a class part and there's a method part setup. And when you have multiple agent, you gonna have multiple class. And later, we're gonna show that tomorrow or something. So, but anyway, but the main focus is that class definition. Like this is the part you define behavior of agent. And then the behavior of agent also means property of agent. Property of agent means the information agent contains. So when you think about agent, you think about some kind of object moving around. But this already has like information of object, shape, and location, and orientation, and possibly speed, or possibly like a birth date. There's many information. The simplest, the most minimal agent has no information. Maybe it has information of time, like when it's born, and this is like 3 seconds after it's born. Meaning, if you want location to exist agent somewhere, you need to give that information as a kind of container of information. So in this case, this agent has 2 information, position and direction. So it's not so library does give you minimal agent which doesn't automatically come with location, event location. For example, for example, agent of gravity, which exists everywhere, does not require location. So it requires a gravitational direction, but no need location. So location is not necessarily the part of information agent. But if you want, but most of agent needs that, so you need to define by yourself. And then the direction as well. Some agent might be omnidirectional or sphere, and if they don't care the location or direction, then you don't need the information. But if you need, you need to define that. So this is the part you are defining the information of agent as a container, and in this case direction position. But if you are thinking about like a three-dimensional object, this agent lacks the information of direction upwards. This is kind of line agent, so they don't care the direction, the kind of rotation, the roll wise. So if you need that, which is up, you will also need that. But this agent doesn't have that information. So, but anyway, first that's a definition of property, and then second part is initialization of the agent. Then technically it's called constructor in object-oriented programming. Constructor is the part which initialize the agent. Usually initialize the property information or data. And like if you set up the position and the direction information, you need to set what that is in the beginning. And then, but also you also need to set up how you initialize the information. Meaning, you can say like any agent starts from the origin. That's design of your agent, and it's fine. But if you want to start from some specific location, somebody else needs to define that information. Then what you do as a designer of the agent or class, you just need to have the system or like a communication protocol of how you get that work, right? Meaning you are opening up the input information with somebody else, or actually you in the future or you later, but you as a programmer to set the information later. So you kind of open up the window to pass the information through. So that's the part this constructor is doing after this parenthesis. So parenthesis is of the function or method is for the input variable to pass through the information. Then, so in this agent, we have two information, position and direction, and then we want both information coming from outside. And then, so we open up the channel to set that two information. And then, so that two information is a vector. So IVEC is IGO library's vector class. So it's three-dimensional vector. And then, so the P is the for position. You cannot, I mean, if you have coding experience, you know that, but you cannot put the same name with this one and that one. So that conflicts. But so this P coming from outside set to the position of the internal information of the agent, and the second one is the direction of that. So this initialize or constructor is used in here, right? So in processing is based on Java language. Java language is object-oriented programming language, and then when you instantiate the class as object, then you use this keyword new, and the name of class creates new object. And then after the class name, you can put two information to pass through the constructor input. So this is the first one is the initial position, and the second one is direction. So that's the framework. And then also this is not important, but I just explained that this ig.b. So ig is IGO library kind of global level method or class. But this is one is supposed to give IVEC data, and usually it's done by like a new and IVEC, because this is creating the instance of vector value, and then new kind of instantiate that. So this is same. Actually, this new IVEC, this ig.v is exact same meaning. This ig.v exists only because it's several letters shorter. That's all. So you can use either. So, but anyway, so that's the instruction, the constructor, and then the third part of the explanation. The update method is the essential part of whole thing. So this is a behavior definition. So agent simulation happens every single time frame of simulation, or like this actually kind of this animation frame. So every time frame, agent update method is executed, and the agent does something, and then keep doing. So they usually like agent simulation or animation simulation in PC, like the time frame is like a 30 frame per second something. So like simulation is done with 30 seconds per second, and then goes on. So then so agent behavior design is actually design of what to write here. Then right now this is the simplest agent. So this one is just keep going straight. And then, but as I mentioned, this is a reproduction based agent. So agent replicates or agent creates another child agent next to it, but next to it exactly to the direction of agent's internal direction, which is this one. So in a way, it copies the agent to the direction of the vector, and they put there. And then next agent create next one, and next agent create the next one. So, and then the another thing you have to actually, so this is a location, this is line, is the line calculating the next agent location. So you know the direction, you know the current position, which is the variable POS, and you calculate the next location, which is just adding the vector of a direction. So that is saved in the variable POS2 and position2. And the same thing for the directions. The child agent direction, I'm gonna keep same because it's going straight. Or I instructed them to go straight. So to instruct straight, maintain the same direction. So then so it's copy. So direction 2 is just copied and then didn't change anything. Then before creating child agent, this is drawing line. So agent doesn't necessarily show any geometry. That's up to you as well. So if you want to show this as line, you need to draw line. If you want to show the points, yeah, you can put points. Circle, if you want, you can put circle, anything. So, but that's so this is a line of the defining geometry for that, and then it just stays. So then finally it creates the agent next to it. So that's the part, create agent, and then finally deleted. Deletion is something tricky thing to think about, which is when child agent is created, if the parent agent stays in the next time frame, this parent agent create another child agent in the same next location. So you're gonna keep creating the next agent all the time in the same location. So if you want the parent agent to create only one child agent, you need to stop this. So in this case, delete it. You need to delete this agent to just have one child. But this next child is gonna become the parent next time, and then next time it's gonna create next. So if you maintain, or if you keep both of them active, they both of them keep producing the same location, so it's gonna be too much. So that's why it's deleted. So then that's why it's going straight. So, but anyway, so that's a mechanism. From here, this is kind of basic framework. Even in the last the clock stack agent later, the basic kind of framework is same. So so I'm gonna then I'm gonna introduce next transformation, like what actually exactly you would do here. So before that, anybody have question? If anybody have question while I'm explaining, you can jump in by just speaking up. So Okay, okay, so then the things to do next is that, okay, I'm gonna move, okay, I want to introduce like a transformation. So right now it's going just straight, right? If you say, what if you want to turn, or if you want to, actually mostly turn, but if you want to go different direction, or if you want to draw some different shape and what to do, that's a question. So I'm gonna just show you the series of commands you can use to change the behavior. So which is basically I'm gonna jump some of that. The main thing is actually rotation. Most of the thing is gonna be rotation. Then exactly what angle and what like what three-dimensional rotation or something. And then but for today also about scaling. So main thing is scaling on the rotation. Although but okay, first let me show this rotation. So this circle thing. So right now I'm gonna keep using this copy pasted code, and I want to just change. So I mentioned the first stage and just went straight because I didn't change the direction. If you want to change the direction, you would give different direction to child agent. And this the dir2, also direction 2 is the direction for child agent. If you don't change this direction, and then child agent won't change. So for example, the thing you could do is like the 2 dot. There's a rotation method called just ROT, and then this is two-dimensional rotation, but three-dimensional rotation. Actually, no, this is three-dimensional rotation. You are supposed to give the axis in the first part, or yeah. So yeah, I'm gonna stick to the example. So if I put this, if I rotate around the axis, which is XY plane rotation, and then you can give some angle, and then angle is not degree but radian, so it's based on like a pi or half pi or a quarter of pi or something. So but in this case of hundreds of pi, and then if I run this code, actually first of all I'm gonna delete this id duration. Then the straight line now changes to circle. And by the way, the basic IGO library operation, we start with as default 4 windows, for views, and then if you want to open one of them, you just double click and to focus on one of them. Later I'm gonna show you start with just one view for animation recording purpose, but the another just IGO operation thing is if you have some geometry in the space, you can type F as a shortcut to focus on that like mine. So, but anyway, that's one thing. But anyway, so this one just changing the rotation or angle, or just inserting rotation command changes the straight behavior to circle. Also, that's easy to understand, right? So. But rotation is one kind of key operation to use, or anytime. But like when to use or when not to use. Oh, actually that's important. But anyway, actually I'm gonna talk about when to use, when not to use later. But for transformation, rotation is one thing. The another thing I can talk about, or important to know for today, is scaling. So. Later in the modular robot project, you wouldn't scale up or down robot unless you ship different size of module, etc. So in that case, that's something else. But today, we are fine with a kind of continuous scaling up and down. So in that case, one thing you can do is scaling, and then this is vector instance. So scaling up and down means multiplying some number to the vector. I mean, there's a scale command as well, but meaning you can double the size of vector by multiplying 2. And then, so multiplying command is called MUL. And then, by the way, multiplying 2 is too much because this simulation or this agent behavior is executed every time frame. So if this multiplying 2 happen 30 times per second, multiplying 2 30 times mean what's that? So multiplying like a 2 and the 4 and the 8 and so 10th frame already 1,000 times bigger, and then so yeah, in that way. So 20 million. So this is much. So when you want to multiply something, usually this is incremental behavior, and the result is exponential. So you just multiply a very small number usually, if it's applied to every single time. So then even 0.1 is kind of huge. So that becomes spiral. I mean, rotation and then scaling up makes a spiral, and then in the other direction, like scaling down means multiplying smaller number that scale spirals inside. Suppose 3. I'd say 0.99 would be something too big. Kind of snail-like spiral. Actually, I wanted to have kind of denser spiral, so 0.999 and create this this spiral. But anyway, so rotation and scaling is a kind of key thing you can do, and then but anyway, just showing the command existing. So rotation and multiplying. Then there's some other geometry transformation operation, and then but you can take other. I mean, there's vector addition and vector subtraction exists, but it's not used frequently. And then another thing might be you can reflect or mirror the vector, although which is kind of actually it's not similar to multiplying -1, but something. And then I mean those are just more example of combination transformation. So combination matters, meaning so currently just having two things, rotation and multiplication. And then, but for example, rotation of half pi, I mean 90 degree. Of course, you can imagine that gonna make a square. I mean, it's tiny, but tiny plus it's scaling down, so it's kind of spiraling down square. Although, because the square is tiny, and then it doesn't. One edge is only like one edge, or like to come back square, it's only 4 times to come down. So you can just change the square multiplication number to be a bit bigger. Maybe still bigger. Still big. But 0.9 would be too much. Yeah. But anyway, so that's the thing. If you then the another thing, I mean, if you are just kind of designing really kind of graphic composition, square is one thing. A square would be one thing, but diamond would be another thing. But making diamond has nothing to do with this behavior. This only matter for kind of local perspective of agent. So this is through eyes of agent. Both square and diamond have 90 degree turn, and then but to make diamond you can do nothing here. You have to do something here, meaning that the initial condition is sometimes important. Although for our space architecture project it might not matter, but for example, if you start with a diagonal line and keep turning 90 degrees, that's gonna be kind of diamond spiral. So So meaning this is also kind of location to control when you design something, but so that's kind of secondary thing to control. Then, but I'm going back. Okay, I'm gonna set this variable back to 100, but just to keep showing more command you could use. Actually, no, this from here I can introduce a if and then actually condition switch to control behavior. But before that, because some of you are be skilled, so if you are interested in like a whole range of commands or classes, what you can do is I have a document of API. So this one, so this is the document section. It has a full class, and then that's actually several hundred. So, but for example, right now, I'm just showing how to see the reference. If you are interested in, if you don't necessarily know how to read the API results, and then you don't need. But just in case, so if you want to see the like a method of this transformation, what you see is first you need to identify the class of the variable. And the class of variable is IBEC. That's the exact name. And then you can just search that IBEC. And then so there's a many variation, but that's like 10 or actually many. So the exact one is IBEC with nothing after that. So IBEC, and then if you click that, it shows the whole set of method. Even for the constructor, there is a variation of that. You can start with no input, and that just make the vector origin, but or 000 vector. Then the method list is here. Like so, there's an addition method. There's a angle method. I mean angle measuring method, and then there is angle measuring on specified plane, and bisector method, center method. Actually, center method is just average, adding whole thing and then average, and then and circumcenter. But anyway, so many vector operations there. So you could use distance measuring that might be used some point. But anyway, so that's how you see, well, you find the reference there. So then if you want to know kind of what's available, so this is the location you can see. And also this reference doesn't only exist on the website. This also is automatically installed when you install Azure library. So if when you install your library, then you unpack the zip file there. There's a reference folder. This includes the exact same in the web page with this. I think this index HTML. Does that? Actually, not this one, but some of them. So it's gonna show the exact same thing. So, but anyway, so that's a reference in case if you are interested. Then going back to the tutorial. So now I want to talk about the if condition. So right now, what transformation to happen is one thing, but when to happen is another thing. I mean that's another level of control. So for example, right now, this is turning 90 degree. Yeah. So one thing you can do is you can change behavior by time, and that is something like a conditional switch. Like well, in some condition you do this, and some other condition you don't do this. So then you can use if condition. That's a kind of general computer programming concept and technique. And then, but so in that case, you need to get the information of time, and then there's a agent local time, and there's also global time. Global time is a simulation time of whole simulation, which was terminated by the ig.duration method. But to know what time currently is, you can use the ig.time that returns the some number. In the first frame, they're going to be 0, and the second is 1, and 100, and some number. So for example, if you want to turn time frame 10, you can put whole transformation code inside here. Then in this case, that happen only at once at a time 10, and then after that just straight. And it's not that interesting, but that's one thing. And then other thing would be from here. It's okay. First, I'm gonna some of operation you can put is like so the time gives you some number, so then you compare with some number. We doing the specific doing something in a specific time is one thing. Doing not doing something at specific time is another thing. So not equal. So if you put not equal 10, time other than 10, you're gonna do the whole thing, but the other that time frame 10, it doesn't do. So in this case, usually rotate around, but okay. So usually rotate around, but at one point, actually, this is 10th time frame. Actually, if start from 0, so it's 11th time frame, it ignores that 90-degree turn and it just goes straight. So when it's ignored, it doesn't transform. Then that means it stays straight. So that's the thing. And or you can rotate around below 10th time frame or before 10th time frame. In that case, it starts with rotation and then it stops rotating and then keep going straight. Thing, and or you can go rotate after 10th time frame. And in that case, it goes straight and it start rotating. That then okay. So that's kind of major 4 thing you put inside the if conditions, like equal or not equal or larger than or smaller than. Then another thing you can do is because this is kind of one-time operation, right? So once you do something, or once you don't do something, or below that, or like before that, after that, that's one kind of switch. If you want to repeat that, you can use modular operation, modular operation. That's a mathematical kind of calculation of like reminder of something when you divide with some number. So percentage 10 means or returns some number which is reminder of division by 10. So if it's 0 to 10, actually no, if it's 0 to 9, it returns same number, because when you divide by as integer, reminder gonna be 0 to 9, gonna be 0 to 9. But if you divide 10 by 10, reminder is 0, so 0 to 9 becomes 0 again, and then 11 divided by 10, reminder is 1, and 12 divided by 10, reminder 2. So this calculates the number from 0 to 9, and it becomes 0 and then 9 and 0 and 9, and so it's kind of a make this as graph type of numbers. So if I say if I say 0, every 10th time frame, it rotates. And then, although it might not be that different. Okay, first time frame, it rotate, or it bent, or it turned. So it made this weird thing. And then further time, it's every time 10th time frame. Although as a whole, geometry is not that different from us last time. Although scale was totally different, but better things to do is, like, for example, if time divided by 10 is smaller than 3, and then the result gonna be like you rotate 3 times and you go do something. So it's now very different, right? So but I mean, geometry is totally different, but you understand the operation, right? You understand operation. 3-time rotation, actually, kind of this 3 was key. Or yeah, because when you turn 90 degrees 3 times, it doesn't come to the same location or same direction. It kind of 270-degree turn. So yeah, it goes to the other side. And then so if it's 2, like you kind of can imagine, right? So 9 twice 90-degree turn is 180, so it can go back and forth. And then 1 just creates bigger square, so it's not that interesting. But 3, 4 is kind of similar but a bit different. Well, actually, no, it was totally different. So it's kind of start going whole thing straight because rotate and straight, rotate and straight. So yeah. But anyway, so this is a kind of repetition or repeating condition. So every 10 time frame, same thing happen, but you kind of control the range, right? So this if condition is something important to play with. Then actually I kind of cover the whole range of technique in a way, or important one at least. So okay, I mean this level I don't think I need to explain too much, but I think you know the concept of else. Like if you have if condition, you do something, and then you can also have the else. If you don't do this thing, instead you do this. So that's the else function. Right now, the example I showed so far was just doing some transformation or not. Then you can instead have like doing some transformation. Sorry, or other transformation. Let me show you example. So other operation, I'm gonna rotate. By the way, this was our example of in the tutorial. So later I made a simpler method which doesn't require the axis, so you can just put angle directly as well. But this only, so this assume the rotation happen on XY plane. So, but anyway, so some other time I rotate 1/3 of pi, which is 60 degrees. So I mean that's kind of big change, but okay. This level kind of you start to lose the foreseeability a bit. If you think a bit, taking a while, you kind of can figure out where to go. But yeah, actually I didn't know this is a geometry I'm gonna get. But anyway, so that's the part. That's the time it doesn't apply this operation. So, but actually just to see the similarity from the previous one, I'm gonna rotate on this very small amount. Then now the straight rotation thing kind of slowly goes to this thing, right? And then yeah, suddenly a little bit organic sensibility. But anyway, but also this switching like a two thing, like one behavior and another behavior, plus this is repetitive and also like periodical and some sequence of time, like time frame 0 to 3, 90 degree, and then frame 4 to 10, 100 pi. So created that geometry. So then repeated, and then you also, I mean, see the sense of module because it's repeated, but not one by one repeated, but the group repeated and then transform. So it's kind of it's getting into the sensibility of hierarchy, not really hierarchy, but like a modularity of that, and then but that is the reflection of these two organized, I'm not organized, but two different behavior of that, but still repeated regularly. So regular repetition, but switching and create this result. So, but anyway, so if and else is something, and of course you can, if you code anything, you would know there is a if, not else if exists, and so the previously it was like if or else. So two different conditions. And the very first one, if and nothing. So that was the simplest form. Second form is if and else, two conditions. And then third type is if and else if and else, and you're gonna get three conditions to do some operation. So if, for example, I can put I dot time percent. And if I have like a 0 to 3 one thing, maybe I can have like a 3 to actually no, 0 to 3, 4 to 6 something or 7 or what my name, some number. And actually no, I want to do that's 4 and 5. This smaller than that does not exist that number 6, so it's 0 to no, it's 5 to 4 and 5. So 0 reminder 0 to 3 here, and then 4 to 5 here, and then 6, 7, 8, 9 is here. Second one, I'm not sure what to do. Let me just rotate in different direction. And bigger one, or double size, double amount. Now actually I'm gonna make it much bigger. So and then result, I don't know, I'm gonna say something. Okay, so we have this kink, not the kink, but the bent. It was kind of negating the whole slight bend on upwards, and then that's now going the other way. But actually this does not look too interesting. So let me do the 120-degree turn. Okay, something else. But anyway, so I mean, actually, the result is not that important. The important thing is that you have three functions to control. So, but one thing, I mean, we are getting to the direction of the hierarchy and the modularity sensibility. But one thing is this is kind of a parallel, meaning like it's a kind of three things happening in the same level. So later hierarchy is something else. It's kind of dimensionally, I mean time dimension. So, but anyway, so that's a kind of a things you can do. And another thing you can do actually, so from here, I'm gonna first thing I want to do, I mean today as exercise is that I want you to do practice with that, playing with that, and then design some geometry formation. And then geometry formation means, I mean, this is geometry formation. So, but some complex and interesting. So I'm gonna give several more examples, and I'm gonna ask you to play with this like for 10 minutes or 15 minutes or 10 minutes, and then show me the result. So, that's what we're gonna do. Although waiting for 10 minutes on YouTube Live would be a bit weird, but so okay, let me do that. So let me show you well, I think several more examples or one more technique. When you want to think, actually, if you want to design this geometry formation, and then behavioral interest is one thing, or complexity one thing, but you might want to increase quantity, and the quantity is something you can also control here. You are starting with one agent. If you want, you can start with multiple. So, for example, okay, I mean, you can imagine that you can just have two of them. That's easy, but behavior is the same. Starting from the same, well, actually, defined location, but just two of them. That's not too interesting. Well, actually, making just two would not be interesting, but how about having 100? So, for example, if you want to have 100 of them, you use for loop. This is another key concept in computer programming in any language. But for loop start with 4 keyword, and then usually use the integer variable as counter and the initialize 0. And then you put comparison statement here of like how many, and then the variable counting variable I needs to stay less than 100, make it repetition of 100. Then I plus plus creates the each increment. So if I do that, and if I just run this, it's gonna create 100 agent on at exact same location. So you don't see 100 agent, although they exist there. They just are on the exact same location. So if you want to have 100 in same different hours, if you want to see them out separate agent, you need to locate different location. To locate different location, you need to change the initial location by using the variable I. So for example, so this counting variable I changes the content value from 0 to 100, actually 99. It's 0 to 99, total 100. So then if we use that number here, then that can change the location. And but another thing, now you have 100 agent, but just putting in like a straight spacing one thing, but like repeating the same kind of thing side by side might not be interesting. Okay, before that, side by side is one thing, but one issue, but spacing is another. And about spacing, that's based on this way of writing. So this value, this initial location is changing from like 000 to 1000 to 200 300. If it's too close, you might want to do 000 on maybe next 1000 or 2000. In that case, you are supposed to multiply this counting variable. So in that case, then you change the spacing. So that's one thing. Then another thing, the repeating same direction of agent is boring, is another thing. So if you want to change that or control that, you need to change here 100 agent, and then so you could just put variable I, which make something. Let me just show you that first. And kind of, wait, does it change the direction? Yes, it kind of, wait, not 100%, I mean, kind of yes. But also it make it bigger because this variable I changes the direction from 100 to 110 and 120, 130, 140. That also changes the size of vector as well. So because the agents, the line length of each agent or initial one corresponds to the length of this direction vector as well. So this was only about the direction. It's also about length or size of agent. So so by changing that, by putting this variable here, that's also changing that as well. If you want to maintain, I mean, scaling up is fine, but we would change direction in terms of like rotation. That's more natural way to think. So in that case, better thing to do is you can rotate the vector here as well. So the rotation method can be applied here as well. And then you have like I, and then this is gonna be radian. So like 360 is like a 2 pi, 2 pi is like a 6 point something. So multiply I, which is like a 0 to 99, which will be too much. So make it just smaller. This part is just kind of ballparking, but so okay, this might be too small change. Kind of changing. Although first of all, it's not still this straight straight layout would not be that interesting. And first of all, I want to change spacing, and second of all, I wanna. But yeah, direction-wise, it's changing, and that's one thing. Although the whole layout is not interesting. And but anyway, so that's an example of changing the direction. But in terms of even the location, putting I variable here make the layout just straight line. So what if you want to start from ring or something? In that case, you have to locate the agent in rotational way. So you could do that in the same way with this. You can keep that first vector same, and you can rotate this one. That the initial location is now like a 10, 0, 0, but they're gonna rotate somehow or some amount. So, and actually, this might be I'm just guessing the number which might make the ring. So close. So, but anyway, so that now it's rotation is different, and then direction different, and so now accumulation might be something else. However, this I made the agent to have this spiral down. So spiral down means they're kind of converging to points. So as a whole, it wouldn't change more than that because it's gonna the latest agent is somewhere here staying there and going deeper and deeper. So but that level is like now I start to see the whole layout and something I might want to do, I might not want to do, and they start changing the variable, and you can guess what to do at that point. For example, I'm start not liking the converging like a spiral down thing, so maybe spiral up might make it more interesting possibly, and the factor or the exact command making everything spiral down is this multiplication. I'm just showing the thought process, but so if I want to scale up and something happen outside or getting bigger and bigger, maybe I need to scale up. So I want to do about 1.1 or I don't know if that's too big or anything. So but anyway, anyway, that's kind of a design process of a whole thing. And then now this is too chaotic, so I might not like too much. So but anyway, that kind of thing is something I want you to do. So okay, and then okay, then what to do is okay. Let me show you one more. Well, two more things. Just for visual purpose. You might want to show nice color or two things. Color and transparency. So that's something you can do. First, color on background. I showed that previously with the command called ig.bg background. So you can put a RGB number 0 to or 000 means black. And one actually there's a two defined command. One takes the integer, another takes a floating point number. If you say 1.0, 1.0, that means white, but you can also put 255, 255. That's white. And yeah, well, if you want to have like a dark blue, that's gonna be like 128. So that's the background. And the foreground, line. Line is actually still not liking the behavior. 1.1. Line color, you can that is something you can change at the location with this curve command. So the name of the command. So you can add method after that. This is kind of a way of writing in IGO library specifically. It's called a command chain. You can do something and you can apply that, and after that you can change some method again. So you can change the color by the command called CLR color. The name actual word color was taken by processing. So you can also put the RGB color here, and then I'm making the background dark blue, so make a white y to be 250. Yeah, 255, 255. Okay, actually, no. I'm going to show you the floating point number version. So 1.0, 1.0, 1.0 is white. But one more thing I can show, which is transparency. First of all, it's white, and yeah, not too great. Okay, so then transparency is something you can add in the fourth number. So the RGB and alpha. So there's also integer version which is maximum 255, but the alpha version or not floating point version, floating point number version, that's 0 to 1, and the transparency is 0.5 is 50% transparency. And then especially when you have too many lines, the transparency works well. If you have like lines separated, you don't need to make it transparent. But if you kind of have too many in the same location, that's something you can take advantage of the density of geometry. So yeah, and then I'm gonna make the rotation small, but not too small. Then one more thing, yet another thing you can do is that this one is to spare. But anyway, another thing, one more thing you can do is that okay. So now you have color control and you have behavior control, and then okay, actually no, I was thinking about changing the color by time, but I think I'm gonna keep leave that for assignment. So let's focus on the geometry. So okay, now I'm gonna ask you to do some exercise of making some interesting geometry layout by this algorithm. So then we're gonna take maybe 10 minutes or so, like right now, I mean in Japan it's 5 p.m. almost. So like 5:10 or like in 10 or 20 minutes, I'm gonna ask you to show your exercise. So then yeah, so let's work on that. But before that, if you guys have any question about this? If not, yeah, get on it, and then yeah, I'm gonna ask each of you to show the result of exercise. Okay, and then let's wait. In the meantime, I'm gonna try mine, and then because yeah, I keep the live streaming, and I'm gonna keep changing my example. So okay, let's see. And I forgot to save. Okay, guys, let's finish the exercise, and then I'm gonna go to student's name, and then please show me the exercise work. Okay. Okay. First, Ina, shape. Can you show yourself? Wait, let me stop my screen first.
Yes. I'm just going to share my screen right now. Can you see it? It's not that impressive. I've seen what you have been doing in the background, but it's, yeah, I was just tweaking some setups around here. And it's very difficult to understand what to do if I don't do it in steps. And for me, I'm used mostly with dimensions. So I find it very tricky to control them in a step-by-step manner. So I guess I need more practice with it.
Sure. Yeah, that's most of the stuff is counterintuitive, or at some point, yeah, it's just not possible to imagine or understand or predict what's gonna happen. But anyway, yeah, just but you're gonna sense, at least you understand like the discrepancy of like what you see in the process or like instruction and then the result. So that's kind of a thing we are passing. So all right, great, thank you. Next, okay, next, wait, Giuseppe, do you have capability to show your PC screen?
Yeah.
Oh, yeah, can
Yeah.
you show? Yeah. Right, go ahead.
Let me see if I can share my screen. So yeah, basically what I was trying to do, sorry, I keep have this problem with Zoom. I hope you can see my screen. I can see my black screen now.
Oh, I see that now. Or it's appeared. Or yeah, I see that now.
So basically, I was trying to, play around a little bit with the code and yeah, starting to play something concentric and maybe do some, but yeah, I'm still just playing around with that really.
Sure. All right. All right, good. Thank you very much. Next, Aroni, can you show your exercise?
Hi, yes, I'm very new to this platform, so I was just trying to understand. So
yeah, that's no problem. Yep.
Yeah, I just did like pattern like this. I was just tweaking around. I'm sorry, I was just following your lecture while you were doing it. So I still have to understand the pi thing happening. So yeah, I don't really have anything to show. Sorry.
Fine. Yeah, by the way, the rotation and the pi, you don't need to use that number necessarily. Like, where is it? Yeah, rotation, you don't need to use pi. Pi is just a 3.1 something number. So it's okay to put like a 0.2, for example.
Thank you. I'll look into it. Thank
Sure.
you.
Yeah, just maybe for everybody, like whatever. If you in the kind of design phase or schematic phase or just idea phase, putting whatever number might then see what happens is still kind of a good thing to do. So yeah, for example, like I was playing with my, wait, actually, first of all, I'm not sharing my screen, so let me share that to talk about what I'm talking. So okay, for example, like so I was playing my code and I was using some rotation something, but like sometimes just putting whatever number or like 0.1 and actually that's devastating. So like rotation not to pi something, but like 0.5 something. Putting random number and see what happens in one approach you can take in this kind of work. Okay, that I didn't know that makes that kind of a start thing. But anyway, so yeah, so sometimes the putting random number works. So when you don't understand, just play with it, and then most of the time it just generates chaos. But sometimes that's something interesting, and then try to go back into the code and see what was that or which part was causing, and then keep doing will produce some good example, good work sometimes. So, but anyway, all right, okay, thank you very much, and then let's move to next person. Okay, next, Shoko, can you show your stuff?
Okay. When I look at it large, I wanted to look like a seashell and animal. When I look at it small, I want it to have fine movement. I want to make it look like a rainbow by changing the color according to time and the movement of the mouse cursor. I'm working now. Thank you.
Wait, I think you share the screen of a coding part of processing and didn't show the
Sorry.
animation. So can you
Sorry.
run that again? Okay, I see that now. Good.
Right.
All right. Looks good. Okay. Then next, Jerun, can you show your exercise?
Sorry, I'm still getting familiar with processing, so I just tried your codes on the processing. So I actually don't have anything of mine to show you guys. Sorry.
Okay, then that's all right. All right, good. Okay, then that case we move on. Okay. Do I have everybody? I think I have one person, but anyway. Okay, then let me continue the tutorial part and then show you some other one more topic like the branching thing. So okay, let me share my screen again. Okay, so then the branching. So now I want to move on to branching. However, okay, the code I want. Okay, first of all, I'm gonna save my code. Sometimes you keep writing processing and forget to save the code, and you either crash or you keep changing, and but you want something you had like a minute ago, and then you don't have it anymore, and you forget what you changed. So in that case, it's good thing to save frequently, or if you find something you like, you should save as another file. Well, anyway, so okay, first I have actually, so now I want to save as another one. And I also I want to keep this, and I want to save as a different one as a branching. So okay, I have this now. Where is it? So I have this now, and then okay, I don't know what happened, but anyway, so I have this, and then for branching I want to keep just one agent. So actually I can either delete for loop, or I can just say number of agents to produce is 1. So then, so I have this agent and I mean weird shape. For branching, branching means you create 2 child, that's all. Or actually, multiple child in this reproduction-based agent system. So current agent system is so parent agent create 1 child, and this 1 child becomes a parent, and they create 1 child, and then 1 child, and 1 child. So, but to branch out, you need 2. Well, could be 3, but when you create 1 child, you also create another one in different direction. I mean, same direction, just create the same overlapping agents, but you create different direction, then you create another child. So the basically, so currently this line is the exact moment agent is generating child agent. So if you want branching agent, you need 2 of them. But again, that's currently you are creating 2 child agent in exact location, in the same location, in exact same direction. That's a big problem. So what you need is you need to change direction. So this direction 2 is first child direction. So if you want another one, you need direction 3, and then I give that to the second child agent. Actually not position 3, direction 3. So then kind of it. Let me show you what happened. It's not actually ideal thing to happen. Okay, first of all, I just stopped agent simulation, although it's still going. Did it stop? It didn't stop. By the okay, there's one issue that I generated 2 child agent per 1 parent, and that's so in the screen you kind of see too many agents, and then that is because first agent create 2 agents, and second, I mean 2 agent create 4, and 4 and 8, and in 10 time frames 1,000, more than 1,000, and then millions, and then so exponential. This is exponential growth. So when you think about the branching, you one thing you need to remember is you can not to frequently if you maintain the total number to be not exponential. So one thing you can do is you don't generate branch as frequently as like this. So every time frame. So what if it's every 10th time frame or something? So for example, so I can use this if condition like above, and if and I dot time like every 10th time frame, if it's equal 0. This expression is something we use in general in computer science frequently to use like periodically, like not so the if condition I showed above was some kind of range of period, but if you when you use like a one time, you usually use this equal, and then if you don't really care what exact moment, like maybe just once every 10 or every 100, usually use like equal 0, like so then this percent the number after the modular operation percentage symbol, this is a period. So every 10th time frame, this happened once. So that's kind of a typical expression of code. But anyway, so not every single time frame, but every 10th time frame we make branch. That's what this code is doing. Then let me see. Kind of makes sense, but still like at this point too many. So if this is too much, maybe I can maybe 30, every 30 time frame, which is like every second or something. Yeah, so it's more like branching. So, but anyway, so the thing is, I mean, branch generate exponential instances or agents. So it's a bit important to control is one thing, but before that, just branch is just as simple as creating two childs. That's all. So that's one thing. But beyond that, of course, there's a control of the transformation, and then when you are playing with those like geometry as a graphic and then kind of as an expression or the design product, yeah, you kind of need to control the branching direction or size or geometric transformation. So then at that point you kind of need to do something similar to those things, and then either you could do something similar to this, like you can copy and paste, and you can have whole another set about direction 3. That's one thing you can do. Although this happen only like once 30 times, you could do this inside here. This part is gonna be executed only when you are not generating child, although it's not a heavy process, so it's okay to have there. But another thing would be like you can, if your operation is simple, you can put transformation method here as well. You can just put them together and it still works. So if you want to like rotate like 0.5 is what, like a 3.14 is 180 degrees. So 30 degrees or something, but then something. So if you just want to rotate some, and then you can do this like this. So then yeah, it's a kind of bending outward, branching out 30 degree ish. You want more, maybe 1.0 be like 60 degree, a bit less. So, but anyway, so yeah, that's it's branching and it still maintains the main behavior. So yeah, that's one example. Just main agent operation, work out the primary child transformation operation, and then branching out secondary transformation operation, which is just rotating 1.0. So, but anyway, so that's branching is that simple. Just create another agent at some the specific time frame. Then okay, additional topic or side topic. If you want to have more, I mean, not too regular branching, you can use random number, or you can use random percentage. And then I want to show you the method of random percentage. There is a random number method in Azure library called iRand. I mean, yeah, iRand, and then there is a percentage method. In short, just I mean percent works, but percent works, but I have the shorter method name, PCT, and you can put like percentage like 0 to 100, and then that makes this if condition to go in 50% of time randomly. So stochastically or statistically, that it change it has a behavior. Then so for example, actually 50% like every other time, which will be too many branching, so chaotic. But like 5%. So this does not make the branching too regular. and this make it irregular. I mean, still after a certain time frame that's chaotic, but maybe 1%. So, I mean, this is just another coding technique of controlling the branching and by time and by probability. So, yeah, that's branching. Then, but anyway, so this is a basic. I mean, actually that was a agent behavior. That's a basic mechanism of the branching. But one more thing about the branching, which is not that simple, is the collision. Collision is not a simple thing. It's a bit trickier thing. So I'm gonna explain that, which is, first I'm gonna save this. So, okay, before moving on to the collision detection, which is about the interaction of agents. I mean, agents need to check other agent location to find out if it's colliding or not. So just to wrap up this section, actually this tutorial page, I wanna say, I mean, the thing I talked about is on this page, all of them, or supposedly, and then like actually one more thing, like a periodical control is something here, and actually this was periodical control is like here, and then random percent is here. There's also random number generator you can also use, which I mean, if you want to turn or rotate randomly, you can use random number. Also, this might not be ideal for modular design. Modular design usually kind of predetermined. The angle is predetermined at the joint, except it has when they have variable angle joint. Anyway, so that's yeah. If you want to look back, you can refer this page and to for the stuff I talked today, and then yeah, the for loop stuff here. This also about for loop, but this is using sine and cosine to define the first location. But anyway, so yeah, but this is the page of the kind of reference point of the stuff we talked today. Then now we move on to the next section, which is about the interaction. And then this one is talk about the interact method. So what I want to do now is if I save this file, and I want to save as another file. To talk about the collision detection, I need to talk about the interaction agent. And the interaction agent is, as a concept, a big one, as important as update method, or as important as like behavior agent, or at every time frame. Actually, interaction is just another behavior. And then, so there's two behavior or like a method in agent, which is kind of general, but which is also specific to the agent I set up in Azure library. So the agent in Azure library has two methods to define the agent behavior. One is update, which we saw so far, and another is interact. Interact is specifically to see other agents and then decide what to do. So to collision detection, agents need to see other agent and then check the distance, or like check the location of the other agent, and then the own agent, and then compare the distance to see if it's colliding or not. So, or if it's line agent, if you might want to check that if the line is intersecting or not. Well, there's many different ways to determine the collision, and then some of them are point based and distance, and some of them are interaction based, and some of them are like Boolean overlap based or something. some more. Yeah, there could be some more advanced one. But but before going to that collision or specific collision detection, one thing I need to say is that, okay, I want to start with some example code, which, not this one, not this one, this one. Okay, okay, this time I'm gonna just copy and paste the this code and then talk about this. So let me do that. This is inside, wait, it's a third code page, actually no more than 1, 2, 3, 4, 5, fifth code in this tutorial page, and I'm gonna copy and paste. Actually, I don't use this one, I just overwrite the whole thing. So what's happening here? Okay, it's first let me run this code. And so this is a branching agent with a 60-degree branching angle, and then they have that collision detection, and they just keep going. So they have a duration of 120. So, but anyway, important thing is how they knew they are colliding, or how they stopped there. So that's the thing. But before that, I need to explain the mechanism of interaction in this specific Azure library agent mechanism. So the key is this interact method. So this still has update method inside this agent, and then this agent is called line agent. Then the branching part is here. So actually, this has this doesn't generate 2 child agent for branching. This generates 3 at once. Although it was controlled by the random percentage, although the method is now using the percent. So okay, so that's a 3-way branching, and then so other than update method, there is a interact method, and the interact method is usually a bit long or complicated, and so you see a lot of for loop and if condition here, although it's just 3, 4, 5 if and 4. But the main difference of this interact method is this has input data or input argument here, and update didn't have any. It was empty input, and this has one input, which is agent, actually list of agents. So this contains the other agents in this variable. So what's happening is actually if you are not familiar with Java language, array list is the series of data, and then if you know Python, this corresponds to list, and yeah, so it's a variable length array of this class, which is not important. This is actually type of, actually it's a parent class of agent, so type of agent. And so, but anyway, the important thing is this is a list of agents. So if you want to check what other agents are doing, you can look into this variable. So then interact method is the place to do that. But problem is that okay, then if you want to know if you are colliding to other agents or not, you need to check everyone. There's no natural way to know if your agent are close or far until you actually check the number, or more precisely check the distance, or comparing the x coordinate and x coordinate or something. So meaning you have to iterate through all of agents to know if any of them are colliding. So there's no skipping of that, although there's some other computer science kind of technique to accelerate that part with the sacrifice of memory space or something. But anyway, so what I need to do to check the collision, I need to iterate through all of the agent, and I need to check the distance of all of them. Then if it's too close, I would say this is colliding. So it's not that kind of black and white thing. In this case, if it's distance-based collision detection, you kind of need to know that the number. Like if this is like closer to the like a distance is more than 1 meter or 30 centimeter, you would say this is colliding. I mean, it's distance collision, so distance point-based collision detection. So it's a spherical distance area. So if your module size is like a 30 centimeter cube, and if it's kind of but corner is longer than that, so but some number need to be defined. But so we just say some number. In this case, the some number is clearance. Okay, clearance is, I'm saying like somehow 1.22, no 1.99 is the number. I say this is colliding. So I'm gonna check that distance with all of the agent, and then if it's smaller than that, I'm gonna say it's colliding. So, but again, so I'm gonna go through each category now. Before that, because this one will be a bit kind of boring part, or kind of super logical and then not visual, and then sometimes difficult to understand part, or not difficult to understand, but just a boring part. I want to say that for the design project or our workshop project, this part is not necessary necessary to work on the project, because this part I wanna give it a template, and then you can just use. This part is something you for your future skill development. I mean, not specifically for IGO agent code, but in general, when you develop agent-based system, and if you need to do like not only collision detection, but any interaction agent, any like a inter-agent behavior needs to happen by this kind of mechanism. So finding agent to communicate with, I mean, if you keep communicating with very specific agent, you can just remember who is your partner or something. But if you need to change the behavior based on the current condition and finding partner agent, or sometimes partner agent is environment. Like you find ground, specific ground, or if you have an agent system, you are searching something, but if you encounter the river is agent, and well, that's weird. But in that case, you need to check the environment exists, and if you find it, you want to do something, and but that kind of so this is kind of framework for any type of the agent interaction. So that's why I'm talking about, and then so if you kind of go through kind of conceptual level, and then that's fine for today or for this workshop. So that's what we're doing. Then yeah, go ahead.
Sorry, I have a question. You were mentioning the some ideas about the forces, and I was wondering if those can be simulated with like real-time examples in terms of gravity and other performances that can be calculated through it.
Sure. Yes, and then forces, I mean, type of agent, but the one thing is that our agent, well, okay, in this library, there is a force kind of system setup, but they can influence only on particular agent. Meaning, the thing we are doing right now is reproduction based. Well, actually, the thing is, okay, first thing is, so the agent in this page does not take any force. They don't move. They are not supposed to move. They are kind of fixed. But the stuff in this section is all particle based, and they are always open to be moved by other forces. So it's kind of foundation, design of foundation of agent system. If your agent ever move, then you would start with a particle based system. Even the modular architecture design. Actually, this workshop I'm not planning to do that because that kind of gives extra complexity to work with. Because, for example, if you move this module and this force need to be transferred to the next module, and you kind of need to think about the transfer of a force, etc., or structure kind of strength and capacity, or how to break, etc. This time we don't deal with that. But if you want to deal with that, you would you maintain the mobility of each vertices or module or something, and then you define the kind of connection something. But anyway, if you want to play with the forces, and then kind of as a starting point in as exercise in processing in IG library, yeah, this page has a whole example, so you can do that, and then well, even when I was once I was playing with force-based geometry for facade design. Although this doesn't mean the facade panel moves, it's actually virtually moving to find the optimal shape. So that's what's doing here. So in this case, facade panel transformable, it's influenced by the force field. And at some point I fixed that whole thing, then they generate the geometry for facade design. Actually, that's what I kind of did in the Amazon college project. But anyway, so.
But what were those performances in this case? Is it fabrication related or
no? This is
structural integrity.
Actually, that could be part of. Okay, first in the actual project, yeah, actually the thing as I mentioned in the presentation, that the collision. Actually, collision is a kind of super simple thing, but that still can be problem, or just it can be solved by the force. They just kind of repulsion force can separate. And then smoke evac. Actually, smoke evac could be some post evaluation thing, not directly inside the simulation process, but you could redefine like smoke evac. So if it's too close, you can increase or adjust the force field to make sparse. That's something possible to do. So, but that's the extent. That's the extent I use this system for that actual project. I mean that specific project. But it's possible to do those. So if you check the structure and integrity, although in this virtual level, each step of the evaluation you need to calculate by yourself, and you need, if you want to do that in real time, you need to also design the feedback system. If this is force-based deformation system, you need to give feedback of structure integrity as a force. Or, for example, if some panel component have joint stiffness parameter or something, then if some structure simulation phase, somehow it gives a feedback to that changes the parameter. That's kind of a good agent system. But anyway, so in that case, you need it's possible. Plus, what I have in example is kind of general force interaction system. But at some point, when you start think about your kind of project, if you want to think about the structure, etc., you need to have each information channel. If you want to have the structure check or performance, like if it's facade, if it's solar performance evaluation, you want to involve inside that, you need to have that simulation or calculation, and you also need to have a channel to give feedback to agent, either as force, either has some internal parameter change, or something else. I don't know. So, well, you could have. I mean, but anyway. So, but in this case, you design the type of agent. If it's either like a structure structure evaluation agent, some other agent, or kind of internal thing of the panel, or one big thing, or how many agents and how many parameters there and how they communicate. That's a thing kind of you need to design whole thing. And the interaction is one kind of key thing to actually especially talk each other in real time. So however, if you have like a structure, one big structure simulation or structure evaluation agent, what this guy needs to do is just to know all the panel agent. So it's not that difficult. Actually, in this case, you don't need the interaction. Actually, you do need interaction, but you just need to know everybody. That's all the panel. And then the interaction is important when you have like a dynamic environment, like a participating agent is always changing, and then there's some encounter of multiple agent or multiple type of agent. The agent type A kind of migrates here, and agent type B migrates here, and they kind of meet here, and then something happens. In that case, you constantly need to check when they meet and what to do. So that's the framework we are looking at. So, but anyway, good question. Right?
I would like to add to that. Do you have a tutorial in your website that where real-time data interacts with the code as a feedback loop?
Interactive with what information? Real time?
Like the real-time data. Like if I say want to work with temperature data or wind data, and it's like and interact with the animation.
Animation is one thing, but okay, for example,
or the design here.
First, I don't have that exact example. Then there's several things you would do is that, for example, if you have like wind data, if you have like an agent simulation and the environment and then wind data, you want to simulate the agent behavior under wind data. What you're gonna do is okay, first of all, yeah, I don't have the example. But second, what you would do in that case is that you have agent, like a whatever agent, or insect agent, something, a robot agent, and you have wind data or wind maker agent, one agent, environment agent, actually one novel environment agent. You make this, and you make this agent, wind agent, to keep generating the wind like every time frame. So this agent would read that like text file or some number file, which has like a wind data of every second or every minute or something, and keep posting this wind data, and then give this wind data to all the agents, or either wind agent give all the data to agent as false, or this individual agent ask the wind agent what's the current wind. So same thing can happen for temperature agent or something. So that's one possible setup. So, but in this way you can do. And I don't have example, but in the past some students I read the tweet data from processing. Actually, it's not IGO library. There's a whole other way to read with real-time information, not like environmental information, but real-time information from social media to newsfeed to video or something, and then doing something that kind of technique exists in the processing world, not ideal world. So processing is much bigger, and there's many kind of video artists, interaction artists, and the data scientists, data engineers there. So there's a kind of a plugin to library to do that. So, but yeah, so but yeah, that's kind of a abstract response, but that's kind of the way you see. So does that answer your question?
Yes, it does. If you have any suggestions, web links, that would be great. I mean, if it's not too much to ask, if you know which library in particular is popular by SciArc students or generally.
Right. That's actually no. That's something you get in the top 10 when you Google. So that's how they do. But anyway, but environment like at least for like a solar simulation. So I did that in the past, for Morphosis project to do the solar analysis, and then again I don't have example, but I have one class to give you solar direction in specific location at specific time. And then I think it's somewhere. I mean, I'm just pointing the reference. So if you want, you can use this. You can use this like. So this class can give you like the direction over the vector of sunlight in a specific year, in specific month, specific day, specific hours, either daylight saving or not, minute, second. So actually, that's how I simulate the. Wait, I have the. Do I have the image? That's how I design the morphosis fair tower facade. Wait. Okay, this thing. So I control the whole panel angle based on the solar direction, but the way I did was I checked every second of the sun direction in front of panel and pick the highest sun and then change or optimize the locate or angle of the facade of that. So I use the for loop to go through 1 year, like every second. Actually, it doesn't need to be every minute of that. So you can do this. So okay. Then other stuff. Other than that, yeah, it's a bit. So there's not much specific reference for that. But general, like a whole range of processing. Processing is much bigger, kind of covering area of the not area, but the thing to think about. So you can get a general processing textbook that could be that would show some like a video technique to text processing data analysis data visualization technique to even network. I think that it's covered there. Or some of the book. Or main book is I think written by the K series. So I mean the creator of the processing, one of the co-creator. So yeah, I think that would be helpful to look into. Also connecting that library and putting other program and putting this IGO library is a bit of work. So that's a bit about the beginner level. So when you get through it and then you get to understand how to connect them together. So that's how, right? Yep. Okay, then let me finish the rest of the code part. Okay, I'm gonna just talk about this and then I'm gonna give you assignment which is not that different from what we did last time. The process, although that I'm gonna ask you to do the branching, try to do that branching as well. So, but anyway, so okay, let me go through this part quickly. So conceptually, not too technical. And then, so what you need to do is go through individual agent and then to check the distance or to, yeah. So then one thing is when you think about agent interaction, you need to think about what you would do or what you let other agent to do. Then when I'm checking collision detection, when collision happens, you have choice of deleting other agent or deleting yourself. And then for some reason, I'm deleting myself. When you find other agent existing, and I don't delete other one, I delete myself. I think one is that this one might be old one, and this might be connected to other. So it kind of removing in the middle of the agent would be weird. So I delete the new one, or this one is not really instantiated or created yet, so disappear. So what that means, this collision detection is checked in the beginning when new agent is created or about to be born. So this happens only once in the beginning, meaning the time, this one, equals 0. So this is different from the ig.time. ig.time is a global simulation time. Just time inside the agent is a local time since the current agent is created. So So this is the very beginning of the kind of iteration. So in the beginning, and then you need to go through all the agents. So that's the second line, the for loop that goes through all the agent inside the list. And then another thing is you would need to narrow down the type of agent you are interacting with. You might, inside this agent input, it might contain many things. Actually, this is everything. So you might have, actually currently there's only this type of agent, line agent, but when you are having the multiple agent, you might have the gravity agent, to weather agents, to ground agents, to insect agent or whatever. So you need to narrow down what agent type is you are interactive with. And then in Java, you need to do something called casting. It's just technical thing to just to make this agent, general agent looking thing into specific agent, and which is not that important. But one more important thing is this list of agents contain everybody, including yourself. So you have to check if the agent you are checking is not yourself. So that's why this line of if line agent not equal this exists. This keyword, I mean Java language specification has this keyword. This means the agent instance itself, the current class instance. So if other agent is this, if you are checking the distance between you and you, it's always 0 and it's always colliding. So you have to exclude that case. Then now finally you can measure the distance. So distance method is this point 2 is other agent location, and then current agent is this PT2. This one has a slightly defined information container from the last one, last class. But anyway, so this is a part actually measuring the distance, and if it's smaller than something, you wanna say this agent is colliding. And then actually, so this is the moment you could delete yourself, the agent you can delete itself, but there's some kind of complicated reason that the timing issue that should not happen now, and that should happen in the update method. So once this is marked, this is colliding by changing the variable called is colliding, usually which is usually false, and it says truth, and then that's a Boolean operation true or false variable. Then later it's deleted inside update method. But anyway, so that's a kind of, I mean, that was super technical description or explanation of that, but kind of concept actually, one a bit technical concept is that you need to check all the agents, you need to check the type of agent, you need to make sure that's not yourself, and then do something. So that's then, okay, so the tutorial is, that this is at the end of tutorial, and let me just go back to the page where we were. So what we do. So one thing I ask you to do one assignment, which is actually do the kind of small design work, which is this agent simulation line drawing work. Oh, actually, I forgot to show you one more technique. Then actually, I want to ask you to also play with branching. However, I don't need you to do too much. Actually, first of all, I don't need you to do the collision detection. That's quite tricky to integrate with what we are doing before. Actually, possible, but some change need to happen. So you don't need to do the. I just want you to. This is not. I just want you to try some branching. I mean, to the level. I mean, without collision detection. So to the level just branching, like one more, what could be two more, and then so that, and then but if the result is not interesting, you don't need to submit that version. So then, but one thing I want you to also play with is that, I mean, just as an extension from the exercise you did today, I also want you to play with the color changing by time. Okay, so I want to show you that technique. To change color by time, so you just need, not just, but you need to change the variable, this variable, by time. That's all. So, but there's several steps. First of all, you can just use this as your time. But one problem is that this variable changes from like a 0 to like a 1 or 2 and 100 and 1000. But the color, it's taking 0 to 1 or 0 to 255. So this will be too big. So I need to change the scale. I need to scale down properly. For example, this if I multiply 0 to 0.01, that changes 0 to 1 in 100 time frame. So 0 was kind of bluish or cyan color, and then 100 and white, and after that just stay white. Actually, the changing number is one thing, but using like a subtract number from that is another thing. So in this case, starting with 1, but it decreased to 0 through time. So changing to publish, but grading. But okay, so this is one step. But another step is that this kind of this is one directional gradient. It stops at one point and doesn't change anymore. So if you want to change that kind of through time, well, repeatedly, using sine and cosine is kind of good idea. So I just put in something without knowing what's going to happen. So I kind of want to make this in blue. So when you use a sine and cosine guide, that keeps the color changing all the time. So then you don't need to make multiply same number in multiple sine and cosine. If you change some of them differently, that kind of changes a combination of those. So but anyway, so playing with this like sine and cosine and in time and color will be something you can play with to pursue some design or called layout, I mean graphical line drawing layout, and it might be interesting, though mine is not that interesting. Anyway, so that's the I think that's a wrap up. So assignment, generate interesting line drawing with color with this agent, and possibly with branching if it's interesting. If it's not interesting, you don't need to branching. So that's assignment. Any questions about assignment? Good. Okay. Then yeah, we're gonna just review in the beginning tomorrow. So anyway, okay. Then I'm gonna send. I have your email, so I'm gonna send you this code I used today or I saved today later on email, so you can use that. This is slightly, I mean, not different from the tutorial as concept, but the specific number is different. So okay, then I'm gonna see you tomorrow at the same time. Is that good? All right. Okay, then thank you very much for participation today, and then I'm gonna see you tomorrow. All right. Bye-bye.
Thank you.
Thank you.
Thank you.